From morning coffee runs to sweet indulgent treats, few foods are as iconic as Dunkin Donuts, McDonald's breakfast, and Krispy Kreme donuts. Behind their comforting familiarity lies a world of industrial baking, precise engineering, and large-scale production. This journey reveals how everyday favorites are crafted in factories and kitchens, blending tradition, automation, and consistency to feed millions daily. The story of Dunkin Donuts began in 1950 when William Rosenberg opened the first location in Quincy, Massachusetts. His vision was to provide high-quality coffee and donuts quickly and affordably, catering to workers looking for a convenient breakfast. The brand grew rapidly, expanding nationally and then internationally, eventually becoming one of the largest quick-service chains in the world. While individual stores once produced donuts on-site, modern Dunkin' systems rely heavily on centralized production facilities and commissaries that prepare donuts in large batches before they are delivered daily to outlets. This shift to centralized baking ensures consistency, efficiency, and food safety at a scale that would be difficult to achieve if every location produced donuts independently. The process begins with raw ingredients, the most essential of which is flour. Flour is typically sourced from regional mills that produce high gluten varieties suitable for yeast-raised donuts. Gluten strength is important because donuts require a dough that can expand and hold air pockets during proofing and frying, creating the light, fluffy interior consumers expect. The flour arrives at commissaries in bulk trucks and is stored in large silos equipped with pneumatic conveying systems that deliver the flour directly to mixing machines when needed. Alongside flour, sugar is a critical ingredient both for sweetness and for feeding the yeast in raised donuts. Sugar is also delivered in bulk and carefully weighed by automated systems. Other ingredients include dried milk solids, shortening or vegetable oils for richness, salt for balance, eggs or egg replacers, and specialized donut mixes that may contain dough conditioners to optimize texture and shelf life. Yeast is essential for the production of yeast-raised donuts, while chemical leaveners such as baking powder are used in cake donuts. Flavorings like vanilla and nutmeg are often incorporated for signature profiles. All of these raw materials are inspected on arrival to ensure they meet quality specifications, with testing for moisture, purity, and microbial safety. Mixing is the first major transformation step. Large horizontal mixers, sometimes called spiral arm mixers, combine flour, water, sugar, yeast, and fats into a homogeneous dough. The dough must be mixed to a specific level of gluten development, which gives it enough elasticity to expand without becoming tough. Mixing time and temperature are carefully controlled, since yeast activity begins as soon as the ingredients are hydrated. For yeast donuts, the dough emerges as a smooth, slightly tacky mass that is ready for fermentation. Cake donut batters, on the other hand, are much looser and resemble thick cake batter rather than bread dough. For yeast-raised donuts, the next stage is fermentation, also called proofing. Dough is placed into large troughs or hoppers and kept in temperature and humidity-controlled chambers. The yeast consumes sugars and produces carbon dioxide, which inflates the dough and develops flavor. Proofing times can vary, but typically the dough rests for 30 to 60 minutes until it has doubled in size. Automated proofing systems monitor conditions precisely to ensure consistent results across batches. Cake donut batters, being chemically leavened, bypass long fermentation and proceed directly to depositing. Shaping the donuts is accomplished by specialized forming equipment. For yeast-raised varieties, dough is sheeted and cut using rotary cutters or stamping machines that punch out rings, bars, or other shapes. Scrap dough is collected and recycled into subsequent batches. For cake donuts, depositor machines extrude batter directly into hot frying oil through ring-shaped nozzles, instantly forming the characteristic donut shape. jelly-filled or cream-filled donuts are typically cut as solid discs without holes. Modern forming machines can produce thousands of donuts per hour, each with an identical size and weight to maintain uniform cooking times. Frying is one of the most critical steps in donut production. Industrial fryers, often designed as long troughs filled with hot vegetable oil, cook the donuts as they move along conveyors. The oil is maintained at a precise temperature, usually between 180 and 190 degrees Celsius, to ensure that the exterior forms a golden, crisp crust, while the interior remains tender and fluffy. Donuts float on the surface of the oil, and automatic turning devices flip them halfway through to ensure even cooking on both sides. The time in the fryer is short, often less than 2 minutes, but during that time, the transformation is dramatic. The dough or batter puffs up, moisture rapidly evaporates, and a rich golden brown surface develops. Oil quality is carefully monitored, with filters removing crumbs and sediment to prevent off flavors. Oil is replaced regularly to maintain consistency. Once fried, donuts are conveyed onto cooling racks or conveyors where excess oil drains and the surface temperature drops. At this stage, they are ready to finish. The finishing stage is where Dunkin Donuts showcases its wide variety of flavors and styles. Plain donuts may be dusted with powdered sugar or cinnamon sugar in tumbling drums that evenly coat the surface. Glazed donuts are passed through glazing waterfalls where a thin curtain of sugar glaze envelops the donut, creating a shiny, sweet coating once set. Frosted donuts are topped with chocolate, vanilla, or strawberry icing applied either by enrobing machines or by automated depositors that spread a uniform layer across the surface. Decorations such as sprinkles are applied immediately after frosting, while the surface is still tacky. Automated sprinkling machines drop measured amounts of colored sugar or chocolate sprinkles, ensuring even coverage without waste. Filled donuts, such as jelly or Boston cream, are injected with fillings using pneumatic filling machines. These machines use nozzles to pierce the side of the donut and deposit a measured dose of fruit preserve, custard, or cream into the center. Each filled donut is checked by weight to confirm the correct amount of filling. Quality control is constant throughout finishing. Workers and automated vision systems check for uniform size, even frying color, complete glaze coverage, and accurate filling. Donuts that are misshapen or improperly coated are discarded or sent to waste recovery. The finished donuts are then arranged on trays or packaged into transport containers for delivery to retail stores. Centralized production facilities typically operate overnight, producing donuts in large batches that are delivered to Dunkin outlets each morning. Trucks equipped with racks or crates transport the products under controlled conditions to maintain freshness. At the store level, donuts are displayed in cases for customers, often alongside freshly brewed coffee, which has become as important to Dunkin's identity as its donuts. Behind the scenes, Dunkin's donut production is an example of large-scale industrial baking. Every step, from bulk ingredient handling to automated frying and glazing, has been engineered for efficiency, hygiene, and consistency. Factories operate under strict food safety programs, including HACCP protocols, allergen control, and sanitation schedules. Workers wear protective clothing and follow hygiene rules to prevent contamination. Equipment is designed for easy cleaning, with stainless steel surfaces, automated cleaning in place systems, and oil filtration loops. The automation does not diminish the artistry, however. Dunkin offers seasonal and specialty donuts that require customized decoration or limited time flavors. These may involve hand finishing steps in commissaries or store-level icing and topping. The variety keeps the brand fresh and appealing, while the core processes ensure the signature taste and texture remain constant. From a sensory standpoint, Dunkin Donuts' success comes from its ability to balance lightness and indulgence. The yeast-raised donuts deliver a pillowy interior with a slightly chewy crust, while cake donuts provide a denser, more flavorful bite. The frying process gives both styles a characteristic richness, while glazes and fillings add layers of sweetness and texture. All of these qualities are engineered into the production system through careful control of ingredients, dough rheology, frying times, and finishing techniques. Distribution and storage also play an important role. Donuts are highly perishable, best consumed within hours of frying. Dunkin's logistics are designed to ensure freshness, with daily deliveries and rapid turnover at stores. Unsold donuts are typically discarded at the end of the day rather than carried over, reinforcing the brand's emphasis on freshness. The McDonald's breakfast story begins in the early 1970s when franchise owner Herb Peterson created the Egg McMuffin, a sandwich designed to resemble Eggs Benedict but adapted for fast food service. It featured a freshly cracked egg cooked in a ring, a slice of Canadian bacon, American cheese, and a toasted English muffin. This innovation sparked the growth of McDonald's breakfast menu, which expanded to include biscuits, bagels, pancakes, hash browns, and sausage sandwiches. Today, breakfast accounts for a large share of McDonald's daily sales, and its production relies on both centralized food factories and in-store assembly. Take the English muffin, for example. McDonald's does not bake these in-house. Instead, large commercial bakeries supply standardized English muffins to distribution centers. These bakeries use industrial mixers, proofers, and tunnel ovens to produce muffins with uniform size, crumb structure, and toasting properties. Once baked, muffins are cooled, packaged, and frozen or refrigerated for transport. At the restaurant, muffins are stored in freezers until needed, then thawed and toasted in high-speed toasters that deliver consistent browning in under a minute. Canadian bacon, or back bacon, is prepared in large meat processing facilities. Pork loins are trimmed, cured with brine solutions containing salt, sugar, and preservatives, and then cooked or smoked in continuous ovens. After cooking, the bacon is chilled, sliced into uniform rounds, and vacuum sealed into large packs destined for McDonald's kitchens. Restaurants keep them refrigerated and quickly reheat the slices on flat-top griddles as orders come in. The cheese slice used in the Egg McMuffin is American processed cheese, manufactured in large dairy plants. This cheese is formulated for excellent meltability and stable shelf life. It is produced by blending natural cheese with milk, emulsifiers and stabilizers, then heating and homogenizing the mixture before casting it into blocks and slicing it into individually wrapped squares. The cheese arrives at McDonald's locations ready to be unwrapped and placed onto hot muffins or eggs, where the heat melts it smoothly. Eggs are another key component, and they are handled in two distinct ways. For sandwiches like the Egg McMuffin, McDonald's uses whole shell eggs. Restaurants crack each egg into a circular ring mold on a griddle, ensuring a perfectly round shape that fits the muffin. Steam is added by covering the egg with a lid, which cooks it gently and evenly. For scrambled eggs and folded egg patties, however, the supply chain relies on liquid eggs processed in large egg-breaking plants. Eggs are washed, cracked, and separated by machine. The yolks and whites are blended, pasteurized to destroy pathogens, and packaged into cartons or pouches. At McDonald's, these liquid eggs are poured onto griddles or cooked in ovens to create fluffy scrambled eggs or folded omelette-style patties that can be assembled into breakfast sandwiches. Sausage patties are manufactured in industrial meat plants. Ground pork, seasoned with salt, pepper, and spices, is blended in massive mixers and portioned into uniform discs using automated forming machines. These patties are pre-cooked on high-capacity grills or in continuous ovens to ensure food safety and consistent doneness. Once cooked, they are quick frozen to preserve flavor and shipped in bulk to restaurants. Staff at McDonald's reheat them on flat-top griddles, where they develop additional browning and flavor before being assembled into sandwiches like the sausage McMuffin. Hash browns are another hallmark of McDonald's breakfast, and their production is a feat of food engineering. In processing plants, fresh potatoes are washed, peeled, and shredded into long strands. The shreds are blanched briefly in hot water to inactivate enzymes and remove excess starch, which helps achieve the golden, crispy texture consumers expect. The blanched shreds are mixed with small amounts of seasoning and binding agents, then formed into oval patties using hydraulic presses. These patties are par-fried in vegetable oil to set the structure and give them a light golden crust. After par-frying, they are frozen solid and packaged for shipment. In the restaurant, frozen hash browns are deep fried to order in fryers filled with vegetable oil until crisp and hot, ready to be served in paper sleeves. Hotcakes or pancakes are supplied in frozen form from large-scale bakeries. These bakeries prepare batter with flour, eggs, milk, sugar, and leavening agents in huge mixing tanks. The batter is deposited onto heated steel belts or griddles in automated production lines that cook the cakes on both sides until fluffy and golden. The pancakes are then quick frozen and stacked with sheets of paper between them to prevent sticking. At McDonald's, they are reheated in microwave or convection ovens, then served with butter and syrup. Biscuits, available in certain markets, are also produced centrally. Industrial bakeries mix dough enriched with shortening or butter, laminate it to create flaky layers, cut it into rounds, and bake them in massive tunnel ovens. Once baked, biscuits are frozen and shipped to restaurants where they are reheated in convection ovens. Bagels follow a similar centralized process, being boiled and baked before freezing and distribution. Alongside food items, beverages like orange juice and coffee play a crucial role in McDonald's breakfast. Coffee beans are sourced globally, roasted in bulk by suppliers, ground, and vacuum packed to preserve freshness. In restaurants, ground coffee is brewed in calibrated machines designed to produce consistent strength and flavor. Orange juice is pasteurized and packaged by beverage manufacturers, arriving in ready-to-serve containers. Milk and creamers are supplied in portion packs for convenience. The assembly process in restaurants is engineered for speed and consistency. Each component, eggs, muffins, bacon, sausage, cheese, hash browns, and pancakes, has a designated station on the production line. Staff are trained to assemble sandwiches in seconds, following standardized build charts. For example, an Egg McMuffin requires toasting the muffin, cooking the egg in the ring, reheating the bacon, adding cheese, and stacking them in the correct order before wrapping in branded paper. Every step is designed to minimize variation, so a customer in Tokyo receives the same product as one in New York. Behind the counter, holding cabinets and warming drawers play an essential role. Cooked items like sausage patties, hash browns, and scrambled eggs are stored at safe holding temperatures for a limited time, allowing staff to assemble orders quickly during peak morning rushes. Strict time limits prevent items from going stale, ensuring freshness. Food safety is paramount throughout the process. Ingredients are prepared in centralized facilities under HACCP protocols, pasteurized where necessary, and frozen to inhibit microbial growth. In restaurants, staff monitor cooking times and temperatures with digital timers and thermometers. Fryer oil is filtered daily, and cooking surfaces are cleaned on schedule. Eggs cooked to order are held to safe cooking standards, while liquid eggs are pasteurized to eliminate risk. Distribution logistics tie everything together. McDonald's operates a just-in-time supply system, with trucks delivering frozen and chilled ingredients from regional distribution centers several times per week. Restaurants rely on walk-in freezers, refrigerators, and dry storage to keep inventories fresh but lean, reducing waste. This system ensures a steady flow of muffins, eggs, meat, and potatoes to thousands of outlets worldwide. From a sensory perspective, McDonald's breakfast is engineered to deliver comfort and consistency. The toasted muffin provides a chewy base, the egg adds richness, the cheese melts into a creamy layer, and the Canadian bacon contributes savory saltiness. The hash browns supply a crunchy contrast, while hot coffee or orange juice completes the meal. Each element has been refined over decades to ensure it satisfies the expectations of millions of customers daily. The story of Krispy Kreme begins in 1937 when Vernon Rudolph purchased a yeast-raised donut recipe from a New Orleans chef and opened the first store in Winston-Salem, North Carolina. The unique flavor and light texture of his donuts quickly became popular, and the company grew steadily, eventually becoming an international brand. While the recipe has been closely guarded, the processes used to make Krispy Kreme donuts have been adapted for modern production, blending traditional dough-making methods with industrial automation. The process starts with the preparation of the dough. Krispy Kreme relies on specialized donut mixes supplied by large-scale flour milling and blending facilities. These mixes contain enriched wheat flour, sugar, milk powder, leavening agents, dough conditioners, and trace flavoring components that give the donuts their unique taste. The mixes arrive at Krispy Kreme shops in sealed bags or bulk silos. In each shop's back of house, industrial mixers combine the dry mix with water, yeast, and additional shortening to form the base dough. Yeast is critical here, as Krispy Kreme donuts are yeast-raised, which gives them their fluffy, airy structure compared to denser cake-style donuts. The dough is mixed until smooth and elastic, a process that develops the gluten framework necessary for trapping the carbon dioxide produced by yeast. Once mixed, the dough is transferred to proofing cabinets, which are temperature and humidity controlled chambers where the yeast ferments and produces gas. During proofing, the dough doubles in size, becoming light and airy. The careful regulation of proofing conditions ensures that every batch of dough has the same volume, texture, and flavor profile. After the initial fermentation, the dough is rolled out and mechanically cut into rings using rotary cutters. Krispy Kreme's machinery is designed to stamp out perfectly uniform rings at high speed. The distinctive donut holes cut out from the center are also fried and sold as mini treats. Dough scraps are collected, remixed, and fed back into the system, ensuring minimal waste. The cut rings are placed onto conveyor trays lined with parchment or mesh that prevents sticking and allows for smooth movement. Next comes the final proofing stage, where the cut donuts rest in specialized proofing conveyors, often called proofer cabinets. Here, gentle warmth and humidity allow the donuts to rise a second time, reaching their ideal volume before frying. This stage typically takes 30 to 45 minutes, and during this time, the donuts become visibly puffy and delicate, ready to be cooked. Frying is the most visually iconic part of Krispy Kreme production. The risen donuts are gently dropped into a long, shallow trough of hot vegetable oil held at a precise temperature, usually around 180 to 190 degrees Celsius. They float on the surface, and a mechanical arm flips them halfway through cooking to ensure even browning on both sides. The sight of rows of donuts flipping in perfect unison has become a hallmark of Krispy Kreme stores. Frying typically takes less than 2 minutes, during which the donuts puff further and develop a golden brown crust while retaining their pillowy interior. Once fried, the donuts are lifted from the oil and placed on a conveyor belt that carries them through the glazing station. This is the most famous stage of the Krispy Kreme process. A curtain of warm, liquid sugar glaze pours continuously over the donuts as they pass beneath, coating them evenly. The glaze is made from powdered sugar mixed with water, corn syrup, and stabilizers. kept warm to maintain a fluid consistency. Excess glaze drips through a mesh and is collected, filtered, and reused in a closed-loop system to minimize waste. The result is the glossy, translucent coating that cracks lightly when bitten into and melts instantly on the tongue. For donuts that require additional toppings, the glazed donuts may pass through secondary finishing stations. Chocolate or strawberry icing can be applied by enrobing or depositing systems. Some donuts are sprinkled with sugar, candy pieces, or cookie crumbs. Filled varieties, such as custard or jam-filled donuts, are injected with fillings using pneumatic nozzles that pierce the side of the donut and dispense a measured amount inside. Topping and filling stations can be partially automated or done by hand, depending on the complexity of the product. Quality control is essential at every stage. Workers and automated systems check that donuts are uniform in size, color, and coating. Any misshapen or undercooked donuts are removed from the line. The production process is designed to minimize defects, but Krispy Kreme emphasizes visual appeal as much as taste, knowing that customers often watch the production in store. What makes Krispy Kreme unique compared to many donut brands is that much of the production happens visibly in front of customers. Many shops have large glass windows where guests can watch the donuts moving along conveyors from proofing to frying to glazing. This transparency is part of the experience, reinforcing the perception of freshness and craftsmanship, even though highly automated machinery drives much of the process. Behind the scenes, the supply chain ensures that every Krispy Kreme location has the raw materials it needs. Central factories prepare the donut mixes, glazes, and fillings in standardized batches. These are shipped to individual stores on a just-in-time schedule to maintain freshness and reduce storage needs. Temperature-controlled logistics keep ingredients safe, while strict food safety systems oversee every step. At the store level, staff manage the machinery, monitor proofing and frying, and handle finishing. They also prepare seasonal and specialty donuts that may require extra decoration or unique toppings. For example, during holidays, Krispy Kreme often releases themed donuts with colored icings, sprinkles, or hand-piped decorations. These require skilled workers to apply finishing touches beyond what automated systems can handle. Hashing out the engineering, the donut line is an impressive example of bakery automation. It integrates mixers, proofers, conveyors, fryers, and glazing waterfalls into a continuous system that can produce thousands of donuts per hour. Temperature, timing, and humidity are all electronically controlled, ensuring consistency regardless of location. The system is also designed for food safety, with stainless steel equipment, clean-in-place systems for sanitation, and oil filtration units that remove debris and extend fryer oil life. The sensory profile of Krispy Kreme's original glazed is central to its identity. The donut is designed to be eaten warm when the glaze is still slightly tacky and the dough nearly melts in the mouth. The formula balances sweetness, fat, and yeast flavors to create a product that feels indulgent yet light. Achieving this balance requires careful control of fermentation, frying time, and glaze formulation. Distribution also plays an important role. Not all Krispy Kreme donuts are sold in flagship stores with production lines. Many are delivered to convenience stores, supermarkets, and smaller outlets. In these cases, donuts are produced in larger commissary bakeries and shipped daily. Specialized packaging maintains freshness during transport, though these donuts may lack the immediate appeal of those sold warm under the hot light. Marketing and presentation amplify the impact of the production process. The sight of fresh donuts moving under the glaze curtain has become iconic advertising in itself, shared widely on social media and forming part of Krispy Kreme's brand identity. Customers are drawn not just to the product, but to the theater of its creation. To craft Starburst, factories begin with a foundation of raw materials, with the primary ingredients being sugar, corn syrup, hydrogenated palm kernel oil, fruit juice concentrates, citric acid, and natural and artificial flavors. Food-grade colorants such as red 40, yellow 5, and blue 1 give the candy its vibrant, recognizable hues. Sugar, the dominant ingredient, is typically sourced from sugar beets or sugar cane, refined to a fine, white granulated form. Corn syrup, essential for achieving the chewy consistency, is extracted from dent corn and then enzymatically converted into glucose-heavy syrup. This syrup not only sweetens, but also inhibits crystallization, allowing for the distinctive, flexible Starburst chew. Fruit juice concentrates are selected based on seasonal availability and flavor profiles, often involving apple, cherry, orange, strawberry, lemon, and other citrus bases. Each concentrate is filtered and reduced under vacuum conditions to intensify the flavor while removing excess water. Meanwhile, citric acid, either derived from citrus fruits or biosynthesized using Aspergillus niger fermentation, is added to sharpen the tart notes and stabilize the pH level. Palm kernel oil, after undergoing hydrogenation to solidify its structure, contributes to the smooth mouthfeel, acting as a lubricant and textural agent within the candy matrix. All of these ingredients are delivered to the factory in bulk: sugar and corn syrup via silo systems and tanker trucks, oils in heated storage tanks, and flavoring agents in sealed food-grade containers to maintain freshness and prevent contamination. Once inside the facility, the first major step in the Starburst making process is ingredient weighing and batching. Massive computerized batching systems measure exact quantities of each component using load cells and automated valve controls. Sugar and corn syrup are combined in stainless steel jacketed mixing tanks where they are preheated to around 115 degrees Celsius. This begins the process of dissolving the sugar crystals into a homogeneous syrup base. Agitators inside the tanks ensure uniformity and prevent scorching. The heated syrup is then transferred to a vacuum cooker. In the vacuum cooking chamber, the syrup is exposed to reduced atmospheric pressure, allowing water to evaporate at a lower temperature. This technique is critical in candy making, as it prevents the sugar from caramelizing or breaking down under intense heat. As moisture is removed, the syrup thickens into a viscous mass with a specific Brix value, typically between 85 and 90% solids content, ensuring it will solidify into a chewy form once cooled. The exact cooking time and temperature are closely monitored via sensors and control systems linked to the plant's supervisory control and data acquisition platform, or SCADA. After cooking, the thickened candy mass is transferred through heated conduits into a mixing chamber known as a color and flavor cooker, or kneader. Here, hydrogenated palm kernel oil is added to help emulsify the mixture and control the final texture. Food-safe mixing blades, often paddle style or Z-blade types, churn the mass at controlled speeds. This is also the point where colorants, acids, and flavor concentrates are injected. High-precision peristaltic pumps ensure accurate dosing of color and flavor to maintain batch consistency, and the mixer is divided into multiple compartments if producing more than one flavor at a time. For instance, strawberry might be mixed in one chamber, lemon in another, and cherry in a third. Each batch customized with different concentrations of fruit essence and specific pH levels for optimal taste balance. Once the flavor-specific masses are ready, they must be cooled to a workable temperature, typically around 60 degrees Celsius, before shaping. Cooling belts equipped with air curtains and stainless steel rollers gently lower the temperature without causing hardening or premature setting. From here, the candy mass is directed into the forming line, a highly orchestrated system of extrusion, cutting, and wrapping. Extrusion is the next key phase. Using positive displacement gear pumps or auger-driven extruders, The warm candy mass is pushed through stainless steel nozzles with rectangular cross-sections. This creates long, continuous ropes of candy with a consistent width and height, matching the final Starburst dimensions. Servo motors carefully control the extrusion speed to synchronize with the downstream cutting process. If multiple colors or flavors are being co-extruded, special twin-screw extruders equipped with internal baffles can combine two masses into a single, dual-colored strand, which adds visual interest and flavor complexity. The ropes move onto a conveyor equipped with cooled rollers to maintain their shape. A high-speed guillotine cutter controlled by an optical sensor system slices the rope into individual blocks with precise timing. The cutting knives are made from food-grade stainless steel and are lubricated with a microfine spray of food-grade oil to prevent sticking. Each candy piece is now in its iconic rectangular shape, ready for wrapping. Wrapping Starburst is a marvel of mechanical ingenuity. Each piece must be individually wrapped in waxed paper to preserve freshness and prevent sticking. Automatic folding and wrapping machines, operating at speeds of up to 800 pieces per minute, perform this delicate operation with stunning precision. These machines use synchronized mechanical arms to position each candy, fold the wax paper around it using rotary folding drums, and seal it using gentle pressure rather than heat, which might soften the product. The wrapped pieces are then collated by vibratory feeders and assembled into 4-piece packs in various flavor assortments. These grouped candies are fed into a horizontal flow wrapper, where they are encased in the familiar branded packaging film. The flow wrapper uses a combination of rollers, film unwinders, photo eye sensors for alignment, and end-sealed jaws to create hermetically sealed packages that protect the candy from moisture and oxygen. The film is often reverse printed with branding, nutritional information, and batch tracking codes. Nitrogen flushing may be used in some production lines to displace oxygen and extend shelf life. After packaging, each unit passes through metal detectors and X-ray scanners to ensure there are no foreign objects or contaminants. Vision inspection systems verify print clarity, package seal integrity, and correct product count. Random samples are pooled for manual inspection by quality control technicians who assess texture, flavor, intensity, size, and appearance. Finished goods are then loaded into cartons by robotic case packers and labeled with lot codes for traceability. These cartons are palletized by robotic arms equipped with vacuum grippers, stacked in strategic configurations to optimize warehouse space and prevent crushing during transport. Once pallets are complete, they are shrink-wrapped and transferred via automated guided vehicles to temperature-controlled storage areas. Though Starburst is shelf-stable, storing it in a cool, dry environment prevents oil separation, flavor degradation, and textural hardening. From these warehouses, Starburst products are shipped out via freight trucks or distribution centers, eventually reaching retail shelves in supermarkets, vending machines, and convenience stores around the world. What makes the Starburst manufacturing process particularly interesting is the interplay between artistry and automation. While the ingredients themselves are simple, achieving the exact chewiness, vibrant color, and flavor burst that consumers expect requires precision engineered machinery, tight process control, and an unyielding commitment to consistency. The smallest variation in moisture content, mixing speed, or cutting pressure could result in a piece that's too hard, too sticky, or aesthetically flawed. Despite being a candy rooted in simplicity, the industrial complexity behind Starburst underscores the broader evolution of confectionery manufacturing. Today's production lines incorporate real-time analytics, inline spectroscopy for flavor consistency, and even machine learning algorithms that predict equipment maintenance needs to avoid downtime. Some newer factories are experimenting with plant-based colorants and sustainable packaging materials, aiming to meet consumer demand without compromising on quality. There's even ongoing research into using recycled steam and closed-loop water systems to reduce the environmental footprint of candy production lines like those making Starburst. Mentos were first created in the early 20th century and gained global popularity due to their unique texture and intense flavor. The combination of a crunchy outer coating and a chewy interior is what sets them apart, and achieving that contrast requires precise formulation and processing. The base recipe revolves around sugar, glucose syrup, hydrogenated coconut or palm kernel oil, gelling agents like gelatin or modified starches, natural and artificial flavors, food-grade colorants, and glazing agents such as carnauba wax. Depending on the variety, mint, fruit, cola, or sour, the flavoring system will differ, but the core production mechanics remain largely the same. Production begins with the sourcing and handling of raw ingredients. Sugar is delivered in bulk form, typically refined cane or beet sugar, and stored in large silos within the factory. Glucose syrup, derived from enzymatically treated cornstarch, arrives in insulated tanker trucks and is stored in jacketed holding tanks to keep it fluid and at the proper viscosity. Oils are stored in temperature-controlled containers to maintain consistency. Each of these raw materials is subjected to a series of pre-checks. Sugar is tested for grain size and moisture content, glucose syrup for dextrose equivalent values, and oils for peroxide levels and stability. The factory's quality control department samples all incoming ingredients and verifies their compliance with specifications using chromatography, spectroscopy, and other chemical assays. Once approved, the first step in making Mentos centers on the formation of the candy core. Unlike many confectionery items, the chewy center of a Mentos is not extruded or cast, but formed using a process called compression or tableting. But before compression can occur, a slurry is created by blending sugar, glucose syrup, and oils in large mixing kettles equipped with paddle agitators. This mixture is partially cooked to evaporate water and develop the candy's elasticity. Once it reaches the desired consistency, typically with a Brix reading of about 85% solids, it is transferred to a cooling table where it is kneaded to achieve the ideal texture. The cooled mass is then broken into chunks and fed into a granulator, which reduces it into fine, uniform particles suitable for compression. These particles are sieved to ensure consistent particle size, which is critical for proper tablet formation. A binding agent, often modified starch or gelatin powder, is then added to help the particles fuse during compression. The powdered base is then fed into rotary tablet presses, high-speed machines equipped with stainless steel dies and punches that compress the powder into uniform cylinders. Each tablet is subjected to high compression force to achieve the dense, elastic core that is characteristic of Mentos. These presses can produce thousands of tablets per minute, and they feature real-time monitoring systems to ensure weight, hardness, and thickness are within specifications. The freshly compressed tablets are soft and not yet glossy. At this stage, they are known as centers and will undergo further processing to become the finished product. These centers are now ready for the panning stage, a method of coating used to apply multiple layers of sugar and flavor to build up the candy shell. The panning process takes place in large, rotating stainless steel drums called coating pans or Drageses pans. The cores are loaded into the pan, which rotates at a controlled speed while fine sprays of syrup, flavor, and color are applied in successive passes. Initially, a syrup consisting of dissolved sugar and glucose is sprayed onto the tablets using atomizing nozzles. Hot, dry air is simultaneously blown into the pan via air ducts, which rapidly evaporates moisture and causes the sugar to crystallize onto the surface of the tablets. This process is repeated over and over, sometimes more than 30 times per batch, to gradually build up the characteristic crunchy coating of Mentos. During these cycles, food-grade colorants and additional flavoring agents are also introduced. Different panning cycles are used for mint and fruit flavors. For example, mint Mentos typically receive a higher concentration of menthol and peppermint oil in the outer layers, while fruit Mentos require individualized flavor additions like strawberry, orange, and lemon, each blended with acidulants such as citric or malic acid to amplify the taste. Achieving uniform coating thickness, color distribution, and surface smoothness requires expert control of several variables: syrup viscosity, pan speed, airflow rate, and ambient humidity. Most modern Mentos facilities use programmable logic controllers and environmental monitoring systems to automate these parameters and ensure repeatability across batches. The entire panning process can take several hours, as each layer must dry before the next is applied. Operators use inline sensors and visual inspections to check for surface integrity, ensuring that no rough spots or cracks appear as the coating thickens. Once the desired shell thickness is achieved, the tablets undergo a drying and stabilization phase in climate-controlled holding rooms. Here, they rest for several hours, allowing residual moisture to equalize and the structure to firm up. The next step is polishing, a critical final touch that gives Mentos their trademark shine and smooth finish. Tablets are reloaded into specialized polishing pans and treated with a mixture of glazing agents such as carnauba wax and microcrystalline wax dissolved in ethanol or isopropyl alcohol. As the pan rotates, the wax mixture is sprayed lightly onto the surface of the tablets and then buffed by friction as the candies tumble against one another. This step not only enhances visual appeal, but also serves a functional role, creating a moisture-resistant barrier that extends shelf life. After polishing, the finished candies are cooled again to harden the glaze and prevent sticking. They are then conveyed to the packaging area via vibratory conveyors and sorting belts that align them into consistent orientations for loading. Modern Mentos factories use high-speed flow wrapping machines capable of packaging dozens of rolls per minute. The individual candies are fed into paper or plastic film wrappers, which are then heat-sealed and crimped into the familiar cylindrical Mentos roll. These rolls are typically grouped into multi-packs or display trays using robotic case packers and then passed through labeling stations where batch codes and expiration dates are applied using inkjet or laser printing systems. To ensure food safety and quality, each roll passes through a series of automated inspection stations. X-ray machines and metal detectors scan for foreign objects, while vision systems inspect label placement, roll integrity, and seal quality. Statistical quality control sampling is performed by trained technicians who manually test rolls for chewiness, coating hardness, gloss level, and flavor profile using a standardized scoring system. Any deviations trigger a hold on the batch and a review of equipment calibration and ingredient records to pinpoint the source of variation. Pallets of Mentos rolls are finally shrink-wrapped and transferred to the factory's finished goods warehouse, where they are stored under tightly controlled temperature and humidity conditions. Though Mentos are relatively shelf-stable, proper storage conditions ensure they retain optimal flavor, texture, and appearance for months. From there, the products are distributed through regional logistics hubs to retail outlets around the globe. While consumers might simply pop a Mentos into their mouth without much thought, the reality is that each piece embodies a tremendous amount of behind-the-scenes engineering. From the uniform density of the core to the microscopic layering of sugar shell, every step in the process is fine-tuned to ensure consistency at massive production scales. Advanced data analytics platforms are increasingly being used in Mentos factories to track machine performance, ingredient variation, and environmental fluctuations, helping operators predict and prevent quality issues before they occur. The candy's production is also seeing innovations aimed at sustainability, including the use of biodegradable wrappers, energy-efficient panning systems, and closed-loop water recycling technologies. Some manufacturers are exploring plant-based gelling agents to create vegan-friendly versions of the product, expanding the Mentos appeal to a broader market while keeping the signature experience intact. The story of Skittles production begins with the sourcing of raw ingredients. The core of each Skittle consists primarily of sugar, corn syrup, and hydrogenated palm kernel oil, combined with fruit juice concentrate, citric acid, natural and artificial flavors, and gelatin or a plant-based gelling agent, depending on the variety. Food colorants such as Red 40, Yellow 5, Blue 1, and others provide the vivid, rainbow-like appearance, while carnauba wax is used for the final shine. All ingredients arrive at the factory in bulk: sugar in pneumatic tankers or super sacks, corn syrup in heated tank trucks, oils in insulated totes, and flavors and colors in sealed drums to preserve potency and prevent contamination. Once the raw materials are delivered to the facility, they undergo quality inspection. Sugar is tested for purity and grain size using optical sensors and moisture analyzers, while corn syrup is evaluated for its dextrose equivalent to ensure consistent sweetness and viscosity. The oils are checked for oxidative stability and melting point, and flavor compounds are tested with chromatography to confirm identity and strength. Approved ingredients are then routed to ingredient storage silos or intermediate tanks, each connected via stainless steel piping to the central mixing systems. The production of Skittles begins with the creation of the chewy center, which is not molded or extruded like many other candies, but rather formed through a process known as casting or deposition. First, sugar, corn syrup, and oils are combined in large, stainless steel, steam-jacketed kettles. Agitators mix the contents while the batch is heated to around 115 to 120 degrees Celsius. This heating step is critical. It dissolves the sugar, reduces viscosity, and activates the gelling agents that will give the Skittle its characteristic chewy texture. Once the mixture reaches the desired consistency, it is partially vacuum cooked to remove excess moisture, yielding a thick, elastic syrup. This candy mass is then deposited into starch molds, which are preformed trays filled with cornstarch that contains indentations for each candy. Depositing heads, essentially nozzles controlled by servo-driven pumps, release precisely metered amounts of the syrup into each cavity. These molds are then transferred via conveyor into a climate-controlled drying tunnel where they remain for 24 to 48 hours. During this time, water evaporates slowly and uniformly, and the chewy texture begins to set. After drying, the starch is separated from the candy cores using a destarching system. This equipment gently shakes and brushes off the remaining starch, which is collected, filtered, and reused in future cycles. The now formed Skittle centers are tumbled in large rotating drums to smooth their surface before being passed to the next critical step, the sugar shell coating, also known as panning. Panning is a cornerstone of Skittles production and one of the most technically demanding phases of the process. The centers are placed into enormous rotating pans, typically several meters in diameter, where the sugar coating is built up through dozens of thin layers. Each pan spins continuously, and while it does, a fine sugar solution is sprayed onto the candy centers. This syrup typically consists of refined sugar, glucose, water, and sometimes citric acid for tartness. Immediately after spraying, a blast of temperature and humidity-controlled air is directed into the pan, drying the surface and forming a thin, hard layer. This coating process is repeated many times, sometimes for several hours, depending on the desired shell thickness. Different flavor syrups are added at different stages if multiple fruit profiles are being used within the batch. The rotation speed, spray volume, airflow rate, and drying temperature are all managed by PLC-controlled systems that monitor pan performance in real time, ensuring consistency in shell formation. Operators oversee the process via touchscreen HMIs, adjusting parameters based on real-time data and sensory feedback from test samples. Once the shell has reached its final thickness, color is added. This is typically done with 1 or 2 additional layers of tinted sugar solution, each one custom formulated for a specific flavor variant. Red for strawberry, yellow for lemon, green for lime or apple, purple for grape, and orange for naturally orange. These solutions include FDA-approved food dyes stabilized with acidulants and emulsifiers to ensure even distribution and adhesion to the candy surface. The result is a batch of candies, each uniformly colored, with a bright and durable outer shell. Next comes the finishing stage, where Skittles are given their unmistakable gloss. This is achieved using polishing pans and a mixture of carnauba wax and microcrystalline wax, sometimes diluted in alcohol to aid dispersion. The candies are tumbled gently, while a fine mist of the wax solution is sprayed onto them. As the pan rotates, the candies polish each other through friction, creating a smooth, shiny finish. This step also provides a moisture barrier that helps extend shelf life and prevents the candies from sticking together in the package. After polishing, the Skittles are passed through cooling tunnels to solidify the coating and stabilize the structure. Then comes the critical stage of flavor sorting and portioning. High-speed sorting machines equipped with optical sensors separate the candies by color, using burst air jets to redirect them into designated channels. This ensures that each bag or pack of Skittles contains the full assortment of flavors in consistent proportions. The sorted Skittles are then conveyed to packaging stations, where they are portioned using volumetric or weight-based fillers. Each batch is dispensed into the appropriate packaging format, whether single-serve pouches, resealable share bags, or rigid tubes. The packaging film is reverse printed with branding, nutritional information, and traceability codes, and it is fed into horizontal or vertical form-fill-seal machines. These machines form the pouches, fill them with product, and seal them in one continuous motion. Precise temperature and pressure controls ensure that the seals are airtight without melting the product inside. As the packaged Skittles exit the line, they are subjected to a series of inspection checkpoints. Metal detectors, X-ray systems, and vision scanners verify that each package contains the correct amount, is sealed properly, and is free of contamination. Random samples are pulled for quality testing, evaluating chewiness, shell thickness, flavor strength, and visual appearance. Some factories even use texture analyzers and sensory panels to verify that the candies meet brand specifications. Once approved, the packages are collated into cartons using robotic case packers and then palletized by automated stacking systems. Each pallet is stretch wrapped for stability and labeled with tracking information, including production time, line number, and batch code. Pallets are then routed to the warehouse, where they are stored in temperature and humidity controlled conditions to maintain optimal product integrity. Skittles are remarkably shelf stable, but proper storage conditions ensure that the texture remains soft and the colors do not fade. From the warehouse, Skittles are distributed via truck to retail distribution centers, grocery stores, vending machines, and online fulfillment facilities. The journey from raw ingredients to store shelves is timed to ensure freshness and consistency, with sophisticated supply chain software tracking every shipment to maintain inventory and respond to fluctuations in demand. The production of Skittles is not only an example of precision manufacturing, but also one of mass customization. Despite being produced in colossal quantities, every single piece must conform to strict standards of flavor, size, color, and texture. Innovations in data analytics, predictive maintenance, and machine learning are being introduced into Skittles factories to continuously improve yield, efficiency, and sustainability. Energy-efficient drying systems, water reclamation units, and biodegradable packaging research are helping the brand minimize its environmental impact without compromising the product's appeal. In the massive production facilities where Reese's peanut butter cups are made, the process begins well before any chocolate is poured or any peanut butter is mixed. It starts with sourcing two critical ingredients: high-quality peanuts and specially formulated chocolate. The peanuts arrive at the plant in large, tightly sealed containers, having already undergone preliminary sorting at dedicated processing centers. However, the Reese's factory does not take any chances. Upon arrival, each shipment of peanuts is sampled and tested for aflatoxins, moisture content, and flavor quality. Only the best peanuts pass through to the next stage. The first critical transformation begins in the peanut roasting room, a cavernous area lined with continuous batch roasters. These machines look like giant horizontal drums that rotate slowly, while hot air circulates inside, ensuring each peanut is evenly toasted to bring out its natural oils and enhance flavor. Temperatures inside the roasters are tightly controlled, typically between 300 and 350 degrees Fahrenheit, and the roasting cycle can last anywhere from 10 to 30 minutes, depending on peanut size and desired roast level. Workers monitor color readings using optical sensors, making slight adjustments to the roast if necessary to achieve that signature Reese's flavor. Once roasted, the peanuts are transferred via conveyor belts to powerful cooling tunnels. Giant fans blow chilled, filtered air over the peanuts to halt the roasting process immediately, locking in the flavor profile. After cooling, the peanuts pass through a series of magnetic separators and vibrating screens to remove any foreign materials or remaining shell fragments, ensuring absolute purity. Next comes the grinding phase. The roasted peanuts are funneled into industrial grinders, massive machines equipped with heavy-duty steel plates that spin at high speeds. The first grind reduces the peanuts into a rough paste. Then a secondary, finer grind transforms the mixture into the silky, smooth peanut butter that will fill every cup. During grinding, small amounts of sugar, salt, and a plant-based emulsifier are added to stabilize the peanut butter and give it the slightly sweet, distinctly savory flavor that fans recognize instantly. The temperature is carefully managed during this phase, usually kept between 120 and 140 degrees Fahrenheit to ensure the oils remain stable and the texture remains creamy but not runny. The freshly made peanut butter is then pumped into enormous stainless steel holding tanks, where it is kept warm and agitated gently to maintain a consistent texture. These tanks are connected by sanitary piping to the production lines, allowing for seamless and hygienic movement of the peanut butter when it's time to fill the cups. Meanwhile, the chocolate preparation is already underway in a different section of the factory. Reese's uses a specially formulated milk chocolate blend that balances sweetness, cocoa flavor, and a creamy melt-in-the-mouth texture. Bulk chocolate arrives in the form of large solid blocks or liquid tanker shipments, depending on the factory's setup. If solid, the chocolate is first broken down in massive pre-melters, slowly heating it to around 110 degrees Fahrenheit to achieve a uniform, molten state. Once liquefied, the chocolate is pumped into tempering machines, sophisticated systems that cool and reheat the chocolate in a precise curve to stabilize the cocoa butter crystals. This tempering process is critical. It gives the finished cups their glossy appearance, firm snap, and excellent shelf stability. Now, with both chocolate and peanut butter ready, the cup assembly line begins. First, paper cup molds are automatically dispensed onto a continuously moving conveyor belt. High-speed chocolate depositor machines then squirt a carefully measured amount of molten chocolate into each paper cup, forming the base layer. The conveyor belt vibrates gently to help the chocolate settle evenly across the bottom and slightly up the sides of each mold. Immediately after this, the conveyor moves the cups through a cooling tunnel, where chilled air at around 50 degrees Fahrenheit partially solidifies the base chocolate layer. This quick cooling ensures that when the peanut butter is deposited, it won't sink all the way to the bottom of the cup, maintaining the ideal layered structure. Next, the creamy peanut butter is deposited into the center of each chocolate base using precision nozzles. The amount of peanut butter is meticulously controlled by programmable pumps, ensuring every Reese's cup has the same perfect peanut to chocolate ratio. Interestingly, the peanut butter filling itself is slightly cooler than the chocolate, typically around 80 to 90 degrees Fahrenheit, which helps it stay firm during the next stages of production. After the peanut butter is deposited, a second layer of molten chocolate is dispensed over the top, sealing in the peanut butter and forming the upper shell of the candy. Again, careful vibration of the conveyor ensures a smooth, even surface. At this point, visual inspection systems using high-speed cameras and AI algorithms scan the cups for consistency, checking fill levels, alignment, and any surface imperfections. Defective cups are automatically rejected from the line. The filled cups then pass through an extended cooling tunnel where they spend several minutes gradually chilling back down to around 45 degrees Fahrenheit. This staged cooling prevents the chocolate from blooming, a condition where cocoa butter rises to the surface and creates an unsightly white film. Instead, the cooling process locks in that deep, shiny chocolate sheen. Once fully cooled, the cups are ready for packaging. Automated robotic arms gently lift rows of finished Reese's cups and place them into pre-formed trays or directly onto flow wrapping machines. Each candy is enveloped in a thin, protective layer of branded orange packaging film. Heat sealers quickly fuse the edges of the wrapper shut, trapping a pocket of nitrogen gas inside. This inert atmosphere helps prevent oxidation, preserving freshness and flavor for extended shelf life. The wrapped candies are then grouped into multi-packs by high-speed cartoning machines, which fold and seal cardboard boxes around designated numbers of cups, whether it's a standard 2-pack, a king-size 4-pack, or a family-size bag of miniatures. These boxes are coded with manufacturing dates, lot numbers, and other traceability data before being stacked neatly onto pallets. Before the pallets leave the factory, a final quality control check is performed. Random packages are pulled from the line and subjected to a battery of tests, including weight checks, taste tests, visual inspections, and even X-ray analysis to ensure there are no contaminants or structural flaws inside the candies. Only when these samples pass inspection are the pallets shrink-wrapped and labeled for distribution. From there, the Reese's cups embark on their journey through a highly coordinated supply chain. Pallets are loaded onto refrigerated trucks, kept at cool but not freezing temperatures to prevent the chocolate from melting or degrading. Distribution centers across the country receive the shipments, from which they are sent to grocery stores, convenience shops, vending machine suppliers, and even directly to online retailers. What's fascinating about the Reese's production process is how every detail, temperature, timing, movement, is optimized for both speed and quality. The factories are largely automated, with programmable logic controllers and centralized computer systems coordinating every phase, minimizing human error and maximizing consistency. Maintenance crews monitor the machinery continuously, ready to intervene if even the slightest deviation occurs. Yet, despite the heavy automation, a skilled team of chocolatiers, food scientists, and process engineers oversee operations daily, ensuring that the soul of the Reese's cup, the perfect balance of creamy peanut butter and silky milk chocolate, is never compromised. In recent years, new technologies have further enhanced production. Advanced predictive maintenance uses AI algorithms to detect early signs of equipment wear, preventing costly downtime. Robotic packaging systems have become faster and more flexible, adapting to different product formats with minimal reprogramming. Even energy efficiency has improved dramatically, with modern factories recapturing waste heat from the roasting and tempering processes to reduce overall power consumption. The result of all this effort is what you hold in your hand, a Reese's peanut butter cup with the same incredible taste that has delighted generations. From careful peanut selection to intricate chocolate tempering, from the first squirt of chocolate to the final seal of the wrapper, every step is a marvel of precision, engineering, and culinary artistry, ensuring that each bite delivers the unmistakable Reese's experience, time after time. The making of Hershey's milk chocolate begins long before any bars are molded or wrapped. It starts with sourcing one of the world's most essential commodities, cacao beans. Hershey's purchases massive quantities of cacao from regions like West Africa, Central and South America, and parts of Southeast Asia. Upon arrival at Hershey's specialized facilities, the cacao beans undergo strict quality control protocols. Sampling machines pull randomized beans from each shipment, checking for mold, contamination, fermentation quality, and flavor profiles. Only beans that meet Hershey's high standards proceed to production. The first major operation is cleaning. Beans travel through a series of shaking screens, magnetic separators, and powerful air jets that remove debris like sticks, stones, and dust. Once cleaned, the beans are routed to the roasting department. Here, colossal stainless steel drum roasters, each capable of handling thousands of pounds per batch, bring the beans up to roasting temperatures of around 250 to 300 degrees Fahrenheit. This roasting phase is crucial. It not only develops the rich cocoa flavors, but also loosens the shell from the nib, the part of the bean that will become chocolate. After roasting, the beans pass through cracking and winnowing machines. Heavy rollers crack the beans open, and powerful airflows then separate the lighter, papery shells from the heavier cocoa nibs. The nibs are collected and sent immediately into the refining phase. The shells, interestingly, don't go to waste. Many are repurposed as agricultural mulch or used in animal feed. The next transformation happens in the grinding rooms. Industrial grinders crush the nibs into a thick, gritty paste known as chocolate liquor. Despite its name, it contains no alcohol. Giant stone mills or modern ball mills spin tirelessly, reducing particle sizes to less than 100 microns. This grinding process releases the cocoa butter within the nibs, turning the dry nibs into a fluid, rich mass. At this stage, the chocolate liquor is either stored or immediately processed depending on the specific recipe being produced. For Hershey's signature milk chocolate, chocolate liquor alone is not enough. It must be blended with several other ingredients: sugar, milk, and cocoa butter, among others. Hershey's famously uses fresh condensed milk rather than powdered milk, a technique that imparts its distinctive flavor. Tankers bring in condensed milk that has already been pasteurized and quality tested for microbial safety. The milk is combined with sugar in large stainless steel kettles and cooked to form what is known as a milk crumb, a dry, sweet, caramelized powder that becomes the base for Hershey's milk chocolate. The milk crumb, chocolate liquor, and additional cocoa butter are blended together in massive mixers that resemble horizontal cement mixers but are built for food-grade standards. In these tumbling vessels, the blend of ingredients becomes a coarse chocolate dough. This dough is then fed through refining rollers, 5 or 6 massive, polished steel rollers stacked horizontally. As the dough passes through each successive roller gap, it is compressed and sheared finer and finer, reducing the sugar and cocoa particles to just the right microscopic size to ensure a smooth texture. At this point, the chocolate still lacks the silky consistency and full flavor that people expect. That's where one of the most crucial steps in chocolate making enters: conching. Hershey's uses giant conching machines, massive, heavy-duty mixers with granite rollers that agitate, aerate, and warm the chocolate dough for hours. Traditional conching could take up to 72 hours, but with modern methods and specialized Hershey's technology, the time has been optimized without sacrificing quality. During conching, volatile acids and bitter flavors evaporate away, while cocoa and milk flavors mellow and deepen. At the same time, the continuous mixing further reduces any remaining coarse particles and disperses the cocoa butter thoroughly throughout the mass. Temperature control during conching is critical. The chocolate must stay within an exact range, typically between 130 to 180 degrees Fahrenheit, depending on the desired flavor development. Ventilation hoods draw off unwanted volatiles, and sensors embedded throughout the conches constantly report data back to automated control systems, adjusting speed and temperature as needed. Following conching, the chocolate moves into the tempering phase. Tempering is an art and science all its own. Chocolate is carefully cooled and reheated through specific temperature curves to create stable cocoa butter crystals. This gives finished chocolate its snap, gloss, and resistance to melting at room temperature. Hershey's uses continuous tempering machines, which can process thousands of pounds per hour. These machines use a series of heated and cooled zones to guide the chocolate through its crystal formation journey with pinpoint accuracy. Improper tempering would result in chocolate that's dull, crumbly, or prone to blooming, a white discoloration, so this step must be executed flawlessly. Once tempered, the liquid chocolate is transported through heated pipes to the molding stations. There, automated depositors squirt precise amounts of chocolate into endless arrays of molds, some shaped for classic Hershey's bars, others for miniature versions or seasonal specialties. The molds vibrate rapidly on oscillating tables to eliminate any air bubbles and ensure an even surface. The molds then enter a long cooling tunnel, a carefully calibrated environment where the chocolate solidifies slowly and evenly. Inside the tunnel, the temperature drops gradually from around 70 degrees Fahrenheit to about 50 degrees, preventing thermal shock and ensuring that the chocolate sets with a fine, smooth crystal structure. After cooling, the solid chocolate is demolded. High-speed mechanical arms flip and flex the molds, gently releasing the perfectly formed bars onto conveyor belts. At this stage, visual inspection systems equipped with high-speed cameras and AI check every piece for uniformity, detecting even minor surface defects or molding errors. Imperfect chocolates are removed from the line for recycling back into the production process. The next step is packaging. For Hershey's bars, the chocolate rides conveyors into flow wrapping machines. Each bar is enveloped in a tight sleeve of foil and then an outer branded paper wrapper. Modern flow wrappers work at astonishing speeds, often wrapping hundreds of bars per minute with perfect precision. The wrapped bars are coded with expiration dates, batch numbers, and tracking information to ensure full traceability from production through to sale. Once wrapped, the bars are collated into cartons or retail trays by robotic packers, which arrange them neatly in boxes that are then sealed, labeled, and stacked onto pallets. Before shipment, a random sample from every production batch undergoes additional quality assurance tests, including break tests, melt tests, taste panels, and microbial analysis. Only after passing all these checks are the pallets released for distribution. The finished Hershey's milk chocolate bars then enter the logistics phase, moving through regional distribution centers that coordinate delivery to supermarkets, convenience stores, cinemas, and countless other retailers around the world. Throughout the distribution chain, temperature control remains critical. Warehouses and trucks are climate controlled to prevent the bars from experiencing temperature swings that could cause chocolate bloom or textural changes. Throughout the entire factory process, Hershey's leverages advanced automation, continuous monitoring, and decades of chocolate-making expertise to ensure that every bar tastes as iconic and consistent as the last. The level of control is extraordinary. Chocolate viscosity, particle size distribution, moisture levels, and flavor profiles are measured and adjusted in real time using sophisticated inline sensors and laboratory tests. In recent years, Hershey's has also invested heavily in sustainability, working directly with cocoa farmers through its Cocoa for Good program to promote ethical sourcing, better farming practices, and environmental stewardship. This commitment ensures not just the continued availability of high-quality cacao, but also a better future for the communities that produce it. The journey of a KitKat begins with two major components: the chocolate coating and the crisp wafer core. Both are manufactured separately and in parallel streams before being married together into the unmistakable KitKat form. Each ingredient, each layer, and each step is engineered with astonishing precision to create the perfect snap, crunch, and creamy finish that KitKat is famous for. The process starts with the preparation of the chocolate. KitKat's signature coating is slightly different from pure chocolate. It is technically a compound chocolate, specially formulated to give a smooth melt and quick setting properties ideal for enrobing wafers. At factories like Nestlé's York facility in the UK or similar plants worldwide, bulk cocoa liquor, cocoa butter, sugar, and milk solids are combined. The cocoa beans that form the basis of the liquor are sourced from sustainable suppliers, cleaned, roasted, and ground into fine paste months before production even begins. To prepare the chocolate coating, the cocoa liquor is blended with sugar and powdered milk in enormous stainless steel mixers. This mixture is then refined through a series of precision-calibrated rollers, reducing the particle size to around 20 microns, finer than the human tongue can detect. The refining phase is essential to create the smooth mouthfeel KitKat lovers expect. Following refinement, the chocolate mass moves into conching machines, where it is slowly mixed, aerated, and heated. This removes any bitter flavors and unwanted acidity, while promoting the development of a creamy, caramel-like flavor that defines KitKat's chocolate. Temperature control during conching is rigorously maintained at around 135 to 180 degrees Fahrenheit, depending on the recipe. Once the chocolate reaches the right flavor and viscosity, it is moved into tempering units, where it's carefully cooled and reheated to produce stable cocoa butter crystals. Proper tempering ensures that the finished chocolate will have a shiny appearance, a satisfying snap, and resistance to blooming. Meanwhile, in another section of the factory, the production of the wafer sheets is underway. Wafer batter, made from a simple mixture of wheat flour, sugar, vegetable oil, leavening agents, and water, is mixed in giant, computer-controlled vats. The batter is pumped through piping systems directly to high-speed wafer baking ovens, each stretching tens of meters in length. These wafer ovens consist of two continuously moving steel belts that sandwich the batter and pass through a baking tunnel. As the belts travel, radiant heat, conduction, and convection work together to bake the batter into ultra-thin, crisp wafer sheets. Each sheet emerges from the oven perfectly cooked, around 2 to 3 millimeters thick, with a delicate, light texture and a uniform golden brown color. After baking, the wafer sheets are rapidly cooled, using forced chilled air to prevent moisture absorption. They are stacked and transported via conveyor belts to the cream spreading stations. Here, a thin layer of specially formulated filling, a mixture typically based on ground wafer crumbs, vegetable fats, sugar, and milk solids, is evenly spread across the wafers. The filling not only enhances the flavor, but also acts as a structural adhesive, bonding the multiple wafer layers together. Usually, 3 or 4 wafer sheets are stacked, with cream filling between each layer. These multi-layered blocks are then pressed under controlled pressure to ensure perfect bonding without cracking or crushing the delicate wafers. After resting for stabilization, the wafer blocks are transferred to high-speed cutting machines. The cutting process is a masterpiece of mechanical precision. Using laser guides and ultrasonic blades, the blocks are sliced first longitudinally, then crosswise into the familiar slim KitKat finger dimensions. Every cut must be perfect. Any deformation could later disrupt the enrobing process or spoil the iconic snap experience. Once cut, the wafer fingers are ready for enrobing. Conveyors carry them through a chocolate waterfall inside the enrobing machines. A curtain of tempered KitKat chocolate cascades over the wafers, completely coating them on all sides. Excess chocolate is blown off the bottom with controlled air jets, creating the thin chocolate layer underneath that gives KitKat its balanced chocolate to wafer ratio. Directly after enrobing, the fingers pass through a vibrating section of the conveyor to settle the chocolate coating and eliminate air bubbles. They then enter a series of cooling tunnels where cold, dry air, typically kept between 40 and 50 degrees Fahrenheit, slowly solidifies the chocolate coating without causing condensation, which would ruin the texture. At this point, the individual fingers are grouped together. KitKat is traditionally made with 4 fingers to a bar, although mini versions, single fingers, and chunkier variants are also produced. Robotic arms align and group the fingers with exact spacing between them before feeding them into wrapping machines. KitKat's iconic red and white wrapper is a masterpiece of branding and practical design. Wrapping is done using ultra-fast flow wrappers that synchronize perfectly with the grouping conveyors. Each set of fingers is enveloped in foil or a plastic laminate film, which protects against moisture and oxygen while maintaining the crunch of the wafer and the smoothness of the chocolate. The wrapping machines heat seal the edges at high speed, and rollers gently press and fold the sealed packs for that crisp, tight package finish KitKat is known for. As the wrapped bars move down the line, high-speed scanners and cameras inspect each package for correct seal integrity, label placement, and print clarity. Imperfections are detected in milliseconds, and defective packs are automatically ejected into collection bins for recycling. Once the KitKats are individually wrapped, the next stage is boxing and palletizing. Robotic case packers arrange the wrapped bars into boxes or display cartons, which are then sealed with automatic tapers and labeled with tracking information. Each box is carefully weighed and scanned to ensure it matches target specifications before being stacked onto pallets by robotic arms or palletizing machines. Throughout the entire production process, rigorous quality control is applied at every major step. Samples of chocolate, wafer batter, finished wafers, and completed bars are pulled at regular intervals for lab analysis. These tests include moisture content checks, microbiological safety testing, taste panels, and break strength tests to ensure the classic crisp break of a KitKat remains perfect batch after batch. In addition to inline testing, larger batch samples are subjected to accelerated aging studies to simulate how the product will perform over its shelf life. Sensory evaluation booths, staffed by trained taste testers, ensure that every batch maintains the exact flavor, aroma, texture, and mouthfeel that consumers expect. Once the KitKats are boxed and palletized, they are shipped out from climate-controlled distribution centers. Transport conditions are carefully managed to prevent temperature fluctuations that could cause chocolate bloom or wafer softening. Many shipments are refrigerated during summer months or in hotter climates to guarantee the product arrives in prime condition. KitKat's industrial production is a brilliant choreography of automation, sensory science, and quality management. Despite the high level of automation, human oversight remains crucial. Line operators monitor critical control points, adjust machine settings, respond to alarms, and carry out maintenance to keep the lines running smoothly, often 24 hours a day, 7 days a week. Recent advancements have further refined the process. State-of-the-art production lines now incorporate AI-driven predictive maintenance, allowing engineers to anticipate mechanical failures before they happen. Machine learning algorithms also optimize ingredient mixing, cooking times, and cooling profiles, subtly adjusting for real-time variables like humidity, ingredient lot variation, or slight temperature shifts in the facility. KitKat's commitment to sustainability is woven into production as well. Modern factories are equipped with energy recovery systems that reuse heat from the ovens and chillers. Water used in cooling and cleaning processes is recycled wherever possible. Additionally, KitKat's cocoa is 100% sourced through programs like Rainforest Alliance certified farms, ensuring ethical and environmentally responsible cocoa farming practices. Each KitKat bar that makes it into a consumer's hands is the end product of thousands of micro decisions and perfectly tuned processes: baking, layering, cutting, coating, cooling, wrapping, all executed with a level of precision that would make a Swiss watchmaker proud. The crisp snap of the break, the lightness of the wafer, the creamy melt of the chocolate, every detail is the result of decades of research, refinement, and relentless pursuit of chocolate and wafer perfection. Red Bull starts with its formula, a carefully guarded blend of ingredients that deliver its characteristic taste, texture, and functional effects. At the heart of the recipe is water, which serves as the main ingredient by volume. This water is not simply pumped from a municipal source and used directly. It undergoes multiple purification stages to ensure it is free of any dissolved solids, minerals, or microorganisms that might alter the taste or stability of the drink. The purification typically begins with coarse filtration to remove particulate matter, followed by activated carbon filtration to strip out organic compounds and chlorine, then reverse osmosis to achieve a very low mineral content. The final step often involves ultraviolet light treatment or ozonation to sterilize the water before it enters the production tanks. Once the water is ready, the remaining ingredients are prepared. These include sucrose and glucose for sweetness and energy, citric acid for acidity and flavor balance, taurine as a functional amino acid, caffeine as the stimulant, and B group vitamins like niacinamide pantothenic acid, vitamin B6, and vitamin B12. Each of these arrives at the factory in bulk form. Sugars as fine crystals, taurine and caffeine as purified powders, vitamins as either powders or highly concentrated solutions. All are stored under controlled conditions and tested in an in-house quality lab for purity and potency. The creation of the beverage begins with the preparation of a concentrated syrup. In large stainless steel blending vessels, precise amounts of sugar are dissolved in purified water under gentle heat, usually between 50 and 60 degrees Celsius, to speed dissolution without caramelizing the sugar. The glucose syrup, if used in liquid form, is pumped directly into the blending vessel through sanitary pipelines. Once the sugars are fully dissolved, the other functional ingredients, taurine, caffeine, and vitamins, are added in carefully measured doses. This mixing process is critical. Operators rely on automated ingredient dosing systems connected to load cells and flow meters to ensure exact quantities, as even a small deviation could alter flavor or regulatory compliance. Citric acid is then introduced to adjust the pH, giving Red Bull its slightly tart backbone and enhancing stability. Flavors, which are part of a proprietary blend, are also incorporated at this stage. These may include natural and artificial components that together create the drink's distinctive aroma and taste. The mixing tanks are fitted with high-speed agitators to ensure uniform distribution of all ingredients, and the resulting syrup is tested in the lab for Brix, acidity, and flavor profile before moving forward. Once the base syrup is complete, it is diluted with more purified water to bring it to the target concentration for the finished beverage. This final liquid mixture, now containing all flavor and functional components, is chilled to prepare it for carbonation. Carbonation is one of the defining aspects of Red Bull's sensory experience, and it is performed with great precision. The chilled beverage passes through a carbonator where it is brought into contact with carbon dioxide under high pressure. The CO2 dissolves into the liquid with the level carefully controlled. Too little carbonation would make the drink taste flat, while too much could affect mouthfeel or cause excessive foaming during filling. The carbonated beverage is then immediately directed to the filling lines. Red Bull is packaged almost exclusively in aluminum cans, chosen for their lightweight nature, excellent barrier properties against light and oxygen, and recyclability. These cans arrive at the factory in massive stacks of unprinted or pre-printed containers, each one spotless and free from dents or imperfections. Before filling, they undergo a thorough rinse with deionized water or ionized air to remove any dust or debris. The rinsed cans move down the line on high-speed conveyors into the filling carousels. The filling process operates at incredible speed, often hundreds of cans per minute, and is performed in a pressurized environment to maintain carbonation. Each can is filled from the bottom up to minimize turbulence and foaming, then immediately sealed with an aluminum end by a seaming machine. This seam is a precision crimping of the lid to the can body, creating an airtight and watertight seal. Once sealed, each can is inverted briefly to ensure the lid is fully sanitized by contact with the beverage inside, then returned upright. Immediately after sealing, cans pass through automated inspection systems. These use a combination of cameras, sensors, and weight checks to identify any underfilled, overfilled, or defective cans. Any can that fails inspection is automatically rejected and diverted from the main conveyor. Approved cans move on to pasteurization or cold sterilization, depending on the plant's process design. Pasteurization involves heating the cans to a specific temperature for a set time to ensure microbial stability, while cold sterilization uses aseptic filling combined with sterilized containers to achieve the same result without heat. Once the cans are confirmed safe and stable, they head to the secondary packaging area. Here, they are grouped into the familiar 4-packs, 6-packs, or larger cases using cardboard wrap or shrink film. Automated cartoners or shrink wrappers handle this at high speed, often in combination with robotic case packers that load the multi-packs into corrugated shipping cases. The shipping cases are sealed with tape or hot melt glue, coated with batch information for traceability, and then stacked onto pallets by robotic palletizers. The pallets are wrapped in stretch film for stability and transported to a climate-controlled warehouse. Although Red Bull is shelf-stable at room temperature, storage away from excessive heat or direct sunlight helps maintain carbonation and flavor over time. From the warehouse, pallets are loaded onto trucks bound for distribution centers and retailers. Given Red Bull's global reach, many of these pallets also enter intermodal shipping containers for transport by rail or sea to other countries. Throughout production, the emphasis on quality and consistency is relentless. Every batch of syrup and finished beverage undergoes analytical testing to confirm caffeine content, vitamin levels, acidity, and carbonation. Sensory panels taste samples to ensure the flavor matches the established profile. On top of that, microbiological testing verifies that no harmful organisms are present, and shelf life trials confirm that the product will remain stable through its intended storage period. The machinery in a Red Bull plant is highly automated, reducing human contact with the product to a minimum. Operators oversee systems via control rooms equipped with touchscreens that display real-time data on mixing temperatures, carbonation levels, filler speeds, and line efficiency. Maintenance crews work behind the scenes to keep pumps, compressors, and conveyors in top condition, as any downtime on a high-speed beverage line can be costly. Sustainability is also a growing focus in Red Bull production. Aluminum cans are already among the most recyclable packaging formats, and many plants source cans with a high percentage of recycled content. Water purification systems are designed to minimize waste, and heat recovery from pasteurization can be used to preheat water for syrup preparation. Efficient compressors and motors reduce energy consumption, and many facilities work to optimize transport logistics to cut fuel use in distribution. What makes the Red Bull process particularly interesting is how tightly controlled and repeatable it must be. The drink's formula is identical worldwide, which means a can produced in Austria should taste exactly the same as one produced in the United States or Asia. Achieving this level of uniformity across multiple plants requires not only identical recipes and ingredients, but also standardized equipment, operating procedures, and quality control protocols. Every plant is essentially a mirror of the others, ensuring that no matter where it's made, Red Bull delivers the same signature flavor, carbonation, and energizing effect. Every can of Monster begins with its ingredients, and the largest component is water. The water used in Monster Energy production is not simply drawn from a tap, it is subjected to a thorough purification process to remove any dissolved solids, organic compounds, or microorganisms that could affect taste, appearance, or stability. The typical sequence starts with coarse filtration to catch sediment, followed by activated carbon filters to strip out chlorine and odors. Reverse osmosis membranes then reduce mineral content to near zero, creating a blank canvas for the flavor formulation. As a final step, ultraviolet light or ozone is used to sterilize the water before it enters the mixing tanks. Next come the sweeteners, functional additives, acids, and flavors that give Monster its distinctive taste and energy-boosting profile. Cane sugar or beet sugar may be used along with glucose or high fructose corn syrup, depending on the variant and market. These sugars arrive in bulk either as crystalline solids or liquid syrup in tanker trucks. Functional ingredients include caffeine for stimulation, taurine as an amino acid additive, and B vitamins like niacin, riboflavin, vitamin B6, and vitamin B12 to support energy metabolism. Some varieties incorporate plant extracts such as ginseng or guarana, which add both flavor and functional appeal. Acids like citric and sometimes malic acid adjust the pH for tanginess and preservation, while natural and artificial flavors create the unique profile for each Monster variety, from the classic green logo flavor to tropical, coffee-based, and sugar-free blends. The first main step in production is the preparation of the concentrate or syrup. In large stainless steel mixing vessels, sugar is dissolved into heated purified water under gentle agitation. If liquid sweeteners are used, they are pumped directly in and blended. Functional powders like caffeine and taurine are carefully weighed and added in controlled sequences to ensure complete dissolution without clumping. B vitamins, which are sensitive to heat, are typically added later in the process to preserve potency. The plant extracts, if used, are measured and incorporated at specific points, often emulsified, to ensure they disperse evenly throughout the drink. Flavor concentrates, which can be highly potent, are metered into the mix using precision dosing pumps. These concentrates often contain a mixture of flavor oils, sweeteners, and acids in a stable base that integrates easily into the water-sugar matrix. Because Monster produces a wide variety of flavors, the plant must be capable of switching from one concentrate to another with minimal downtime. A challenge that requires clean-in-place systems to flush and sanitize mixing tanks and pipelines between batches. Once the syrup is fully blended, it is tested in the quality control lab for sweetness, acidity, caffeine content, and flavor profile. The lab team uses sensory analysis alongside instrumental testing to ensure the mixture matches the established standard. Only when it passes these checks is it moved forward. The next stage is dilution and carbonation. The concentrated syrup is blended with additional purified water in large batch tanks to reach the target formulation for the finished drink. This diluted beverage is chilled to near freezing temperatures to maximize the solubility of carbon dioxide during carbonation. The chilled liquid enters a carbonator, where CO2 is injected under high pressure and mixed through fine diffusers or inline mixers. The carbonation level is closely controlled. Too little, and the drink will taste flat. Too much, and it will foam excessively during filling. Once carbonated, the beverage moves immediately to the filling lines. Monster Energy is almost always packaged in aluminum cans, chosen for their lightweight, barrier properties, and recyclability. These cans arrive at the plant in massive pallets of unfilled containers, often printed with Monster's signature claw mark logo and variant-specific graphics. Before filling, each can is inverted and passed through a rinser, which uses either deionized water or ionized air to remove any dust or particles. The cans travel into high-speed rotary filling machines, where they are filled from the bottom up to reduce foaming and preserve carbonation. Each filler head dispenses an exact volume, ensuring every can meets legal net content OMA requirements. Immediately after filling, the cans pass into a seaming machine, where an aluminum lid is placed on top and mechanically rolled into place to form a double seam that locks the contents in airtight. This seaming process is a critical control point. Improperly sealed cans can lose carbonation or leak, so seamer performance is constantly monitored. Sealed cans are inverted briefly so that the liquid inside can contact the underside of the lid, which acts as a quick sterilization step. Depending on the plant's process, the cans may then undergo tunnel pasteurization. Moving through a heated water spray tunnel that raises the beverage temperature for a specific time to kill any microorganisms. Or may rely on aseptic filling techniques that eliminate the need for heat treatment. Once pasteurized or otherwise stabilized, the cans are cooled rapidly to prevent heat damage to vitamins and flavors. They then pass through a series of inspection systems. Automated vision cameras check for dents, damaged seams, or incorrect graphics. Check weighers ensure that each can contains the correct amount of product, and any deviation triggers an automatic rejection. Many lines also incorporate inline gas analysis to confirm carbonation levels in the finished product. The approved cans move into the secondary packaging area, where they are grouped into multi-packs. This may involve cardboard carriers, shrink-wrapped bundles, or trays depending on the market. Automated packers arrange the cans in the correct pattern, wrap or enclose them, and send them toward the case packing stage. Here, multi-packs are loaded into corrugated shipping cartons, which are sealed, coated with batch and date information, and stacked by robotic palletizers. Pallets are wrapped in stretch film to secure the load and sent to the warehouse for storage. Even though Monster Energy is shelf-stable at room temperature, it is generally stored in cool, dry conditions to maintain flavor and carbonation quality. From the warehouse, products move through distribution networks to retail shelves worldwide. Behind all of these steps is a rigorous quality control program. The production team pulls samples at every stage: syrup preparation, dilution, carbonation, filling, and post-packaging to confirm compliance with product specifications. Analytical labs test for caffeine content, sugar level, vitamin potency, pH, and carbonation. Microbiological testing ensures that no spoilage organisms are present. Sensory panels evaluate taste, aroma, and mouthfeel to maintain brand consistency. The machinery that makes this possible is heavily automated. Operators work from control panels in climate-controlled rooms, monitoring temperatures, pressures, flow rates, and carbonation levels via touchscreen interfaces. Programmable logic controllers coordinate the entire process, from mixing through palletizing, and sensors throughout the plant send real-time feedback. This automation allows Monster to produce enormous volumes with minimal downtime, while meeting strict safety and quality standards. Sustainability considerations are increasingly built into Monster's operations. Aluminum cans are highly recyclable, and many suppliers provide them with a significant proportion of recycled content. Water purification systems are designed to recover and reuse as much water as possible in non-product applications like cooling or cleaning. Heat from pasteurization is often recovered and used to preheat water for syrup preparation, reducing energy demands. Transportation logistics are optimized to reduce emissions, and some plants have moved towards renewable energy sources for part of their power. What is most striking about Monster Energy production is its consistency. The brand's image may be chaotic and wild, but the drink inside is the product of careful, repeatable processes that leave nothing to chance. Every step is measured, every variable tracked, every can inspected, ensuring that when a consumer pops the tab and hears that sharp hiss of carbonation, they get exactly the flavor, mouthfeel, and energy hit they expect, whether they bought it in a gas station in California or a convenience store in Seoul. The making of a can of Celsius Energy is a study in a modern beverage manufacturing where health-focused marketing meets industrial-scale precision. Although the drink is promoted as a fitness or metabolism-boosting energy beverage, the underlying production process is much like that of other carbonated functional drinks. A carefully balanced formula of water, sweeteners, active ingredients, and flavors blended, carbonated, and packaged under conditions designed to maintain purity, consistency, and shelf stability across millions of units. It begins with the most abundant ingredient, water. Water quality is paramount in Celsius production because any dissolved minerals, organic matter, or off flavors could interfere with the delicate flavor balance and the stability of the added functional ingredients. Purification is achieved through a series of treatments. First, the incoming water is screened through coarse filters to remove particles. Activated carbon filters then strip out chlorine, residual odors, and organic compounds. Reverse osmosis membranes reduce dissolved solids to extremely low levels, creating a neutral base. Finally, ultraviolet light or ozonation is applied to sterilize the water before it enters the formulation tanks. Once the water supply is ready, the functional and flavor ingredients that distinguish Celsius are prepared. Unlike traditional energy drinks that lean heavily on sugar and caffeine alone, Celsius incorporates a blend of caffeine from both synthetic and natural sources, such as green tea extract and guarana seed extract. It also features taurine, B vitamins, vitamin C, and in many varieties, additional plant extracts such as ginger root extract for a warming, metabolism-supporting effect. Some variants are sweetened with cane sugar, while many zero sugar options use non-nutritive sweeteners like sucralose or stevia extract. Acids like citric acid and malic acid are used to balance the flavor profile and help preserve freshness, while natural flavors, often fruit-based, create the distinct taste of each variety from sparkling orange to peach vibe. The first major step in production is creating the base concentrate or syrup. This happens in large stainless steel mixing vessels equipped with high shear agitators or propeller mixers to ensure complete dispersion of both solids and liquids. For sugar-containing variants, crystalline sugar is metered into the purified water and dissolved at a controlled temperature to speed up the process without causing caramelization. If the formula calls for 0-calorie sweeteners, these are introduced in microgram precise quantities via automated dosing systems, as their sweetness intensity is many times greater than that of sugar. Functional powders, such as caffeine, taurine, and vitamin C, are weighed with laboratory-grade scales before being added. Plant extracts often arrive as liquid concentrates or fine powders and may require pre-dissolution in a small amount of water or glycerin to ensure they blend smoothly without clumping. For heat-sensitive ingredients like vitamin C, addition occurs towards the end of mixing to minimize degradation. Throughout this stage, the pH is monitored and adjusted as needed since certain active compounds are more stable within specific acidity ranges. Once all solids are dissolved and liquids are homogenized, flavoring compounds are introduced. These may be natural fruit essences, essential oils, or compounded flavors from specialist suppliers. The flavoring process is highly sensitive. Even slight, over, or underdosing can shift the sensory profile away from the established standard. The completed syrup is sampled and sent to the in-house quality control laboratory for analysis. There, technicians measure sugar concentration, acidity, caffeine content, and other activities, and conduct sensory evaluations to confirm taste matches the reference profile. After passing these checks, the syrup is diluted with more purified water to the final formulation strength in large batch tanks. At this stage, the beverage is chilled to near freezing temperatures in preparation for carbonation. Carbonation is one of the signature sensory features of Celsius's sparkling varieties, and it is carried out with precise control over dissolved CO2 content. The chilled liquid flows into a carbonation unit where carbon dioxide gas is injected under pressure, dissolving evenly into the liquid. The goal is to achieve a crisp, sparkling mouthfeel without excessive foam that could cause filling issues. From the carbonator, the beverage is pumped directly to the filling lines. Celsius is typically packaged in slim aluminum cans, often the 12-ounce or 355 milliliter size, chosen for their portability, shelf life stability, and recyclability. The empty cans arrive at the plant in palletized stacks and are fed onto conveyors. Before filling, they undergo a rinse using ionized air or deionized water to remove any dust or particles. The cleaned cans are inverted, then righted, and sent into the filling carousel. The filling process operates at high speed, often hundreds of cans per minute, and is done under conditions that protect carbonation. Each filler head dispenses an exact volume from the bottom up to reduce turbulence. Immediately after filling, the cans move into a seaming machine, where an aluminum lid is placed on each and mechanically crimped to form an airtight seal. This seam is a critical element of the can's integrity, and seaming stations are regularly checked with seam micrometers to verify proper formation. Sealed cans may pass through a pasteurization tunnel, depending on the plant's preferred stability method. In pasteurization, the cans travel along a conveyor under sprays of hot water that raise the internal beverage temperature to a specific target for a defined time, killing any potential microorganisms. Afterward, the cans are cooled quickly to protect heat-sensitive nutrients. In some plants, aseptic filling technology is used instead, allowing the drink to be filled into sterilized cans without the need for post-fill heat treatment, which can better preserve delicate flavors and vitamins. Once cooled, the cans pass through a series of inspection systems. Vision systems scan for dents, label defects, or improper graphics. Check weighers ensure the net content is correct, and any can outside the tolerance is automatically rejected. Inline gas analyzers may measure CO2 content to confirm carbonation consistency. Approved cans enter the secondary packaging stage, where they are grouped into multi-can packs. Cardboard sleeves, shrink film, or tray packs are applied depending on the distribution plan. Multi-packs are collated into corrugated shipping cases, which are sealed with glue or tape and printed with batch codes for traceability. Robotic palletizers stack these cases onto pallets in stable patterns, after which the pallets are wrapped in stretch film to secure them for transport. The finished pallets move into climate-controlled warehouse storage. Celsius products are shelf-stable, but temperature control helps maintain flavor, carbonation, and nutrient stability over the shelf life. From here, pallets are shipped to distributors, retailers, and online fulfillment centers worldwide. Throughout this process, quality control is constant. Samples from each batch are tested for caffeine level, vitamin potency, flavor accuracy, pH, and carbonation before release. Microbiological tests ensure no spoilage organisms are present. Sensory panels evaluate the finished drink for mouthfeel, aftertaste, and aroma, comparing it to the brand standard. Because Celsius positions itself in the better-for-you beverage category, consistency in active ingredient content is especially critical, and certificates of analysis often accompany each production run. Behind the scenes, this is all enabled by a network of highly automated equipment controlled by programmable logic controllers. Operators monitor the process from control stations, adjusting parameters like mixing speed, carbonation pressure, or filler settings as needed. The plant's clean-in-place systems allow tanks, pipelines, and fillers to be washed and sanitized automatically between batches, ensuring hygiene without extended downtime. Sustainability is an increasing focus in Celsius production. Aluminum cans are infinitely recyclable, and many suppliers now provide cans with a high percentage of recycled content. Plants work to reduce water use in cleaning and cooling, recover heat from pasteurization to preheat processed water, and optimize transport routes to cut emissions. Some facilities integrate renewable energy into their operations, such as solar panels or purchase agreements for green electricity. What makes the Celsius production process interesting is the careful balance between functional beverage science and mass-market beverage engineering. While the plant extracts and nutrient additions require precise handling to maintain potency and stability, the large-scale manufacturing environment demands speed and efficiency. The result is a beverage that can deliver consistent taste, carbonation, and nutritional content across millions of cans, while supporting the brand's positioning as a lifestyle-oriented, health-conscious energy drink. The production of sunflower oil in modern industrial facilities is a meticulously orchestrated process that transforms raw sunflower seeds into the clear, golden oil commonly used in cooking and food production. This journey begins with the careful selection and preparation of sunflower seeds, ensuring that only the highest quality seeds are processed to produce premium oil. Upon arrival at the processing plant, sunflower seeds are subjected to a rigorous cleaning regimen designed to remove a variety of impurities that may have been introduced during harvesting and transportation. This initial phase is critical, as foreign materials such as soil, stones, plant debris, and metal fragments can compromise the efficiency of the extraction process and the quality of the final product. The cleaning process typically involves several stages, each employing specialized equipment tailored to eliminate specific types of contaminants. The first line of defense in the cleaning operation is the magnetic separator. This device utilizes powerful magnets to attract and remove ferrous metal particles from the stream of sunflower seeds. Metal contaminants can originate from various sources, including harvesting equipment and transport containers, and their removal is essential to prevent damage to downstream processing machinery and to ensure product safety. The seeds pass over or through magnetic plates or drums, where metallic impurities are captured and separated from the bulk material. Following magnetic separation, the seeds proceed to vibrating sieves or screens. These machines consist of perforated plates or mesh screens that oscillate at high frequencies, effectively sorting the seeds based on size and shape. Larger impurities, such as sticks, leaves, and oversized debris, are unable to pass through the screen openings and are thus separated from the smaller, uniform sunflower seeds. The vibration intensity and screen aperture sizes are carefully calibrated to optimize the removal of unwanted materials, while minimizing the loss of viable seeds. To address the presence of denser contaminants like stones and clumps of soil, the cleaned seeds are then routed through destoners. Destoners operate on the principle of density separation, utilizing airflow and vibration to differentiate between heavier impurities and the lighter sunflower seeds. As the mixture is fed onto an inclined vibrating deck, air is blown through the material from below. The heavier stones resist the upward airflow and migrate to the higher end of the deck, where they are discharged, while the lighter seeds are carried by the vibration to the lower end for collection. This process effectively ensures that only clean seeds advance to the next stage of processing. After the comprehensive cleaning process, the sunflower seeds are ready for dehulling, also known as shelling. Sunflower seeds are encased in hard outer shells or hulls that constitute a significant portion of the seed's total weight. These hulls are low in oil content and can impede the extraction process if not removed. Therefore, dehulling is a crucial step aimed at increasing the efficiency of oil extraction and improving the quality of the resulting oil. The dehulling process begins with the conditioning of the seeds to facilitate the separation of the hulls from the kernels. Conditioning typically involves adjusting the moisture content of the seeds through controlled heating or humidification. Properly conditioned seeds have hulls that are more brittle and easier to crack, enhancing the effectiveness of the dehulling equipment. Once conditioned, the seeds are fed into dehulling machines, which employ mechanical forces to crack the hulls. One common type of dehuller is the centrifugal sheller, which uses a rotating impeller to hurl the seeds against a hard surface, causing the hulls to fracture upon impact. Another method involves the use of roller mills, where seeds pass between counter-rotating rollers that exert compressive and shear forces, breaking the hulls without damaging the kernels. The choice of dehulling equipment depends on factors such as seed variety, desired throughput, and specific plant configurations. Following the cracking of the hulls, the mixture of kernels and shell fragments undergoes a separation process to isolate the oil-rich kernels. This separation is typically achieved through a combination of aspiration and screening techniques. Aspiration involves the use of air streams to lift and remove the lighter hull fragments from the heavier kernels. The mixture is fed into an aspirator, where a controlled airflow lifts the less dense hulls away from the denser kernels, effectively segregating the two components. Screening may also be employed, utilizing vibrating screens with specific mesh sizes to further refine the separation based on particle size and shape. The efficiency of the dehulling and separation processes is paramount, as incomplete removal of hulls can lead to increased fiber content in the oil, affecting its clarity and stability. Moreover, residual hulls in the meal byproduct can diminish its nutritional value and marketability as animal feed. Therefore, processors often implement multiple passes through dehulling and separation equipment to achieve optimal results, balancing the trade-offs between processing time, energy consumption, and product quality. With the sunflower kernels now isolated and free from their hulls, they are ready to undergo further processing to extract the valuable oil contained within. The next stages involve mechanical pressing and/or solvent extraction, each with its own set of procedures and equipment designed to maximize oil yield and quality. These processes will be explored in detail in the subsequent sections, delving into the intricacies of transforming cleaned and dehulled sunflower seeds into the refined oil that reaches consumers worldwide. Now it's time to go into the core phase of sunflower oil manufacturing, the oil extraction process. This is where the golden liquid locked inside the sunflower kernels is separated and collected. The extraction phase typically uses one of two methods, or more commonly, a combination of both, for optimal oil recovery: mechanical pressing and solvent extraction. Each method has its own benefits and limitations, and modern sunflower oil factories are designed to seamlessly integrate these systems into a continuous, high-efficiency process that minimizes waste and maximizes yield. The first step in oil extraction is mechanical pressing, often referred to as expelling. In this process, the dehulled and cleaned sunflower kernels are conveyed into a series of screw presses, also known as oil expellers. These heavy-duty machines consist of a cylindrical barrel housing a rotating helical screw shaft. As the kernels are fed into the expeller from one end, the screw shaft compresses them with increasing pressure as they travel along the barrel. The space between the screw and the barrel gradually narrows, intensifying the pressure and causing the oil to be forced out through small perforations or slits in the barrel wall. This process is incredibly robust and continuous, with some industrial presses capable of handling several tons of seed per hour. However, mechanical pressing alone can only extract about 85% to 90% of the total oil content from sunflower seeds. The remaining 10% to 15% stays trapped in the pressed cake, a solid, fibrous byproduct that still contains a considerable amount of valuable oil. To retrieve this remaining oil and improve overall efficiency, factories employ solvent extraction. Before the solvent extraction phase begins, the pressed cake from the mechanical expeller must be properly prepared. This involves breaking the compacted cake into smaller, uniform pieces using a cake breaker or flaking mill. The flakes are then conveyed to a conditioning unit where they are heated to a specific temperature, usually between 60 to 80 degrees Celsius. This heating not only helps to soften the cell structure of the material, but also enhances the effectiveness of the solvent by improving oil solubility and fluidity. Once conditioned, the sunflower cake is fed into a continuous extractor, typically a horizontal rotary extractor or a loop extractor. In this large stainless steel apparatus, the cake is soaked with a food-grade solvent, most commonly hexane, which has an exceptional ability to dissolve oils. The cake moves slowly through the extractor on a perforated conveyor belt or through a series of baskets, while the solvent is sprayed from above and recirculated from below. As the hexane seeps through the material, it dissolves the residual oil, forming a solution known as micellar. This micellar, containing both oil and solvent, is then pumped out of the extractor and sent to a series of distillation units where the solvent is evaporated and recovered, leaving behind the crude sunflower oil. The evaporation process is conducted under vacuum and controlled heating conditions to ensure complete solvent recovery without degrading the oil. Simultaneously, the now oil-depleted cake, referred to as spent meal, is conveyed to a dissolventizing toaster. This equipment uses steam and indirect heat to remove any residual hexane from the meal, making it safe for use as high-protein animal feed. Next, let's look at the processing of crude sunflower oil, which, at this stage, is a deep amber liquid that contains several impurities, including free fatty acids, phospholipids, pigments, waxes, and trace metals. Though technically oil, this unrefined product is not yet suitable for cooking or bottling. It must be purified and stabilized through a multi-step refining process, which includes degumming, neutralization, bleaching, dewaxing, and deodorization. The first of these refining steps is degumming. In this phase, the crude oil is mixed with a small amount of water or a weak acid, such as citric or phosphoric acid. This causes the naturally occurring phospholipids, also known as gums, to become hydrated and coagulate into a heavier phase that can be separated through centrifugation. The removal of these gums is crucial because they can contribute to off flavors, reduce shelf life, and interfere with further refining stages. The centrifuges used here operate at extremely high speeds, up to 5,000 revolutions per minute, creating centrifugal forces strong enough to separate even microscopic droplets and particles. Once degummed, the oil is subjected to neutralization, where it is treated with a caustic soda solution to remove free fatty acids. These acids can contribute to rancidity and reduce the oil's stability, so their removal is vital for producing a high-quality, shelf-stable product. The soda reacts with the free fatty acids to form soap stock, which is then separated from the oil via another round of centrifugation. The soap stock may be further processed into industrial byproducts such as lubricants or fatty acid distillates, ensuring minimal waste. Now it's time for the bleaching phase. Despite its name, this stage does not involve any chlorine or harsh chemicals. Instead, the oil is mixed with an adsorbent clay material, often activated bleaching earth or acid-activated bentonite, that binds with pigments, trace metals, and other unwanted compounds. The mixture is then heated under vacuum and passed through a filtration system where the spent clay is removed, leaving behind a visibly lighter oil. The objective of this step is not only to improve the color, but also to remove pro-oxidants and residual contaminants that could impact the oil's flavor or stability. But up next is one of the most temperature-sensitive and critical steps: dewaxing. Sunflower oil naturally contains waxes that, while harmless, can cause cloudiness or sedimentation when the oil is refrigerated or stored at low temperatures. To ensure crystal clear oil, particularly for use in transparent bottles, the dewaxing process is implemented. The oil is cooled gradually in a crystallization tank to allow waxes to solidify, and then pass through chilling filters or plate and frame filter presses. The solidified waxes are captured by the filter media and removed, leaving the oil with improved cold stability and clarity. Finally, the last refining step is deodorization. This process removes volatile compounds, including aldehydes and ketones, that can impart undesirable flavors and odors to the oil. Deodorization is carried out in a high vacuum, high temperature distillation column where the oil is subjected to steam distillation at temperatures between 180 to 240 degrees Celsius. The high temperature causes the volatile substances to evaporate, and the vacuum ensures they are swiftly removed from the system. Modern deodorization systems include structured packing and multiple stripping trays that allow for efficient steam-oil contact with minimal thermal degradation of the oil. The end product of this exhaustive refining sequence is a brilliant, light yellow, odorless oil with a neutral flavor and excellent oxidative stability, qualities that make it ideal for cooking, frying, baking, and use in processed foods. The refined sunflower oil is now ready for bottling or bulk packaging, depending on its intended application, whether destined for supermarket shelves or as an ingredient in snack foods, margarine, or ready-to-eat meals. The oil's journey from seed to bottle is far from over. Now it's time to explore the next critical phase in the industrial sunflower oil production process, the packaging and distribution stage. After undergoing extensive cleaning, pressing, solvent extraction, and refining, the sunflower oil is now fully processed, brilliant in clarity, neutral in flavor, and stable for both cooking and long-term storage. But before it can reach consumers or be used by food manufacturers, the oil must pass through highly automated and carefully controlled packaging systems. These systems are designed to maintain product integrity, optimize shelf life, and meet regulatory and commercial requirements for both retail and industrial distribution. Once the refined sunflower oil leaves the deodorizer, it is pumped into large stainless steel holding tanks. These tanks are equipped with inert gas blanketing systems, typically using nitrogen, to prevent oxidative degradation of the oil. Even trace amounts of oxygen can initiate rancidity, so maintaining a low oxygen environment in storage is critical. The tanks are also thermally insulated and often jacketed for temperature control, maintaining the oil at a stable range of around 25 to 30 degrees Celsius. This ensures that the oil remains fluid and clear, preventing cloudiness that could otherwise form during cooler storage conditions. From these storage tanks, the oil is directed via stainless steel pipelines to the packaging area. The transfer lines are equipped with positive displacement pumps and high sensitivity flow meters to ensure precise, consistent delivery volumes. Before entering the filling systems, the oil passes through final filtration units, often made up of multi-layer stainless steel mesh or polymer filter cartridges to capture any microscopic particulates that may have entered during tank storage. This guarantees that only the cleanest, crystal clear oil reaches the packaging stage. The packaging line is often separated into two main tracks, one for retail-sized bottles, typically ranging from 500 milliliters to 5 liters, and another for bulk containers, such as 20-liter jerry cans, 200-liter drums, or 1,000-liter intermediate bulk containers for industrial clients. The retail packaging line begins with empty bottles being loaded onto a conveyor, either manually or through robotic depalletizers. These bottles are usually made from food-grade PET and are blow molded on-site or sourced from specialized suppliers. Before filling, every bottle passes through a bottle rinser, where a jet of filtered, compressed air or ozonated water is sprayed inside to remove any dust or particles. This ensures microbiological and particulate cleanliness before the oil is introduced. The cleaned bottles are then transferred to multi-head volumetric or gravimetric filling machines. These high-speed machines, capable of filling up to several hundred bottles per minute, are calibrated to extreme accuracy, ensuring every bottle contains the precise labeled volume, no more, no less. The filled bottles are immediately capped by rotary capping machines, which place and tighten tamper-evident screw caps or snap-fit closures. Some systems integrate induction sealing, where a foil liner inside the cap is sealed to the bottle mouth using electromagnetic energy. This creates an airtight, tamper-proof barrier that preserves freshness and prevents leakage during transit. After capping, bottles pass through labelers that apply pressure-sensitive or shrink-sleeve labels. These labels are printed with brand information, nutritional facts, batch codes, and expiration dates using high-speed inkjet or laser coders, allowing for complete traceability of every unit. Following labeling, bottles proceed through automated inspection systems equipped with cameras and sensors that verify fill levels, cap integrity, label alignment, and code legibility. Any non-compliant bottles are automatically rejected via pneumatic arms into separate bins for rework. Approved bottles continue along the line to automated cartoning and case packing stations, where robotic arms place them into cardboard cartons, followed by case sealing with hot melt glue or tape. For bulk packaging, a separate line handles large volume containers. These containers are positioned under filling nozzles that are often suspended from load cells to ensure accurate weight-based filling. Bulk fillers must also incorporate anti-foaming and venting mechanisms to prevent air entrapment, especially at high flow rates. Once filled, containers are sealed with heavy-duty caps or tamper-evident seals and palletized for shipping. All packaging configurations, whether for retail or industrial use, are assigned unique identifiers linked to the master production batch and logged in the plant's ERP system. Now it's time to delve into the logistics and distribution chain, which plays an equally crucial role in maintaining the sunflower oil's quality and ensuring timely delivery to global markets. Once the packaged oil is palletized, it is moved via autonomous guided vehicles or forklifts to climate-controlled storage warehouses. These warehouses are designed for high throughput and efficient inventory turnover. Pallets are organized using barcoded location systems, and warehouse management software ensures that the oldest batches are shipped out first, following the FIFO principle. Transportation from the factory to distribution centers, wholesalers, retailers, or export terminals is typically conducted in temperature-regulated trucks or intermodal containers. For export shipments, ISO tank containers or food-grade flexi tanks are used to transport sunflower oil in bulk volumes over long distances, often across continents. These tanks are insulated and equipped with inert gas blanketing systems to maintain oil stability during the journey. For local or regional deliveries, finished product pallets are shrink-wrapped, strapped, and loaded into trucks equipped with GPS tracking and real-time temperature monitoring. Each shipment includes digital delivery documents with QR codes or RFID tags that sync with customer inventory systems, facilitating seamless unloading and tracking upon arrival. Delivery confirmation, quality checks, and real-time feedback mechanisms are used to verify that every order arrives in optimal condition, both physically and chemically. But up next is one of the most critical dimensions of the modern sunflower oil industry: quality assurance and regulatory compliance. The food-grade nature of edible oil necessitates adherence to stringent quality standards at every stage of the process, from seed selection to final bottling. Every batch of sunflower oil is subjected to a comprehensive suite of analytical tests conducted in on-site laboratories or accredited third-party labs. These tests include parameters like free fatty acid levels, peroxide value, aniseidine value, color, moisture content, and soap residue, all of which provide a comprehensive snapshot of oil quality and stability. Gas chromatography is used to profile fatty acid composition, ensuring the oil meets the standard range for linoleic and oleic acid contents. Spectrophotometers analyze color and clarity, while Karl Fischer titration determines residual moisture. These tests not only guarantee regulatory compliance with international standards like Codex Alimentarius, the European Union Food Safety Directives, and the US FDA guidelines, but also help refine internal production protocols. If any parameter falls outside the accepted range, the affected batch is isolated and either reprocessed or discarded. Up next, we focus on one of the more overlooked yet incredibly vital components of sunflower oil production: byproduct utilization and factory process integration. Modern industrial sunflower oil facilities are designed not only to produce refined oil efficiently, but also to capitalize on every possible output from the sunflower seed itself. This means that even materials which, in earlier generations of oil production, may have been considered waste, are now valuable raw materials for secondary industries or reprocessed within the factory. One of the most important of these byproducts is the sunflower meal or cake that remains after the oil has been extracted. This dense, protein-rich substance is collected immediately following the dissolventizing process and cooled using air blast or counterflow cooling systems to bring the temperature down from over 100 degrees Celsius to ambient levels. This temperature drop is necessary to preserve protein quality and prevent mold growth during storage. The cooled meal is then ground into a uniform particle size using hammer mills or roller mills and passed through vibrating screens to remove any oversized clumps. Sunflower meal is widely used in the livestock and poultry industries as a valuable feed ingredient due to its high protein content and favorable amino acid profile. Factories that produce sunflower oil at scale often have integrated bagging or bulk loading systems for the meal, allowing it to be packaged into 25 or 50 kilogram bags or loaded into bulk silos for shipment in trucks and rail cars. Some facilities even have in-house pelletizing systems that compress the meal into pellets, which are easier to handle, store, and transport. Another byproduct generated during processing is the husk or hull removed during the dehulling stage. These hulls, although devoid of oil and low in protein, have significant value as a biomass fuel. Many sunflower oil factories have transitioned to using these hulls as a renewable energy source to generate heat or steam for use in the facility. The hulls are fed into biomass boilers equipped with particulate filters and emissions control systems where they are combusted cleanly and efficiently. The steam produced powers heat exchangers for oil refining processes like bleaching, deodorization, and dewaxing, reducing reliance on fossil fuels and lowering the factory's carbon footprint. In more advanced facilities, excess steam from the coal-fired boilers is also used to drive small steam turbines, generating on-site electricity that supports lighting, automation systems, and auxiliary equipment. This form of cogeneration enhances energy efficiency and contributes to the plant's sustainability targets. Some operations even sell surplus energy back to the local grid, turning what was once a waste product into a revenue stream. Water recycling is another critical area of integration. Given the extensive use of water in processes such as conditioning, steam generation, equipment washing, and degumming, a closed-loop water treatment system is essential. Wastewater from the plant is collected in large settling tanks, where solids are removed via sedimentation. The water then passes through biological treatment units and membrane filtration systems, such as reverse osmosis or ultrafiltration, to remove organic matter, oil residues, and chemical impurities. The treated water is reused in non-critical applications like boiler feed or equipment cleaning, drastically reducing freshwater consumption. Now turning to process automation, modern sunflower oil facilities operate as highly digitized environments where real-time data governs every aspect of production. Centralized control rooms equipped with HMI panels and SCADA systems provide operators with full visibility and control over temperature, pressure, flow rate, and other parameters at each processing step. Every sensor in the system, from tank-level monitors to flow meters and load cells, is networked to a control system that not only logs data for traceability, but also actively regulates inputs to maintain optimal efficiency. For example, if a temperature deviation is detected in a deodorization column, the SCADA system can automatically adjust the steam valve opening percentage to correct the temperature within seconds. Similarly, in the filling line, digital vision systems detect the fill level and reject any bottles that fall outside preset tolerances. This integration between mechanical systems and digital controls ensures the factory runs continuously with minimal human intervention, reducing errors and improving consistency. Predictive maintenance is another application of advanced automation in sunflower oil production. Vibration sensors, thermographic cameras, and acoustic monitors are placed on motors, gearboxes, pumps, and bearings to detect wear patterns long before failure occurs. The data is fed into AI-driven platforms that analyze trends and forecast the optimal time for maintenance. This prevents unplanned downtime, increases equipment lifespan, and maintains uninterrupted production flow. Inventory management and logistics are similarly digitized. Raw materials, finished oil, packaging supplies, and maintenance components are tracked using barcodes or RFID tags that interface with the plant's ERP system. This allows real-time monitoring of stock levels, automatic reordering when thresholds are reached, and optimized production scheduling based on available resources and demand forecasts. Finished goods are tracked through the entire supply chain, and shipping documents are generated automatically, reducing paperwork and human error. Manufacturing Almond Joy candy bars on an industrial scale begins long before any chocolate is melted or coconut is mixed. It starts with the careful sourcing and preparation of one of the candy's most iconic and defining components, the coconut. This isn't just any shredded coconut. This is a specific, moisture-balanced, finely textured variety that gives Almond Joy its distinct chewy center. Producing coconut to these specifications requires a highly controlled and deliberate process. And in modern facilities, this step alone involves extensive coordination between agricultural suppliers, food scientists, and processing engineers. The coconuts used in Almond Joy bars are primarily sourced from tropical regions like the Philippines, Indonesia, and India, where coconut palms grow in warm, humid climates and are harvested multiple times per year. The coconuts are selected based on strict criteria such as maturity, size, and oil content, all of which contribute to the flavor and structure of the final product. After harvesting, the outer husks are mechanically removed using rotary dehusking machines, exposing the inner brown shells. These shells are then cracked open using high-torque hydraulic presses or mechanical splitters, allowing access to the white coconut meat inside, also known as copra. Once separated from the shell, the coconut meat is washed in large stainless steel tanks using filtered water, sometimes with a light chlorine solution to remove any contaminants, shell fragments, or residual dirt. The clean coconut meat is then graded using high-speed rotary shredders, which reduce it into uniform strands. These industrial shredders operate at several thousand RPMs and are fitted with specialized blades designed to achieve a consistent flake size. The exact dimensions of the shredded coconut are critical. Too coarse, and the texture becomes stringy. Too fine, and it loses its chewiness. The shredded product is then passed through vibratory sieves to remove any oversized or undersized particles, ensuring each flake meets factory specifications. Once the coconut is shredded and sized, it undergoes a drying phase, designed not to fully desiccate the coconut, but to bring its moisture content into a very specific range, typically between 12 and 14%. This drying process is carried out in large belt dryers or fluidized bed dryers that blow heated air over the coconut shreds while keeping them suspended and moving, ensuring even drying throughout. Sensors embedded in the dryer constantly monitor moisture levels in real time, allowing for micro adjustments to airflow and temperature. This precision ensures that the final coconut retains its soft, moist chewiness without being wet or prone to microbial spoilage. Once dried, the coconut is cooled with ambient air and sent through a metal detection system before being packed into sterile bulk totes or drums, ready to be delivered to the candy production line. Now it's time to go into the coconut syrup blending process, where the prepped coconut is transformed into the moist, sweet filling that forms the base of every Almond Joy bar. At this stage, the dried coconut shreds are transferred from storage bins into large stainless steel ribbon blenders or planetary mixers. These mixers are food grade and designed to gently fold the ingredients together without compressing or overworking them, which would damage the texture. While the coconut is being added to the mixer, a separate part of the factory is simultaneously preparing a sugar syrup that will serve as the binder and sweetener. This sugar syrup is cooked in large steam-jacketed kettles, each fitted with agitators and temperature sensors. The syrup typically contains a blend of sucrose, corn syrup, and a small percentage of invert sugar, which helps prevent crystallization and keeps the final mixture smooth and cohesive. The ingredients are combined with water and brought to a boil, then held at a precise temperature of around 230 to 240 degrees Fahrenheit. Once the syrup reaches the desired consistency and viscosity, it is pumped through insulated transfer lines into the mixers containing the shredded coconut. The hot syrup is slowly added into the mixing chamber while the paddles rotate at a controlled speed, ensuring that every strand of coconut becomes evenly coated. This mixing step is closely monitored for torque resistance, an indirect measure of viscosity and saturation. If the mixture becomes too stiff, it indicates that not enough syrup has been added, while an overly slack consistency could suggest too much moisture. Adjustments are made in real time, either by slowing down the mixing blades or by adding additional syrup in carefully measured quantities. The end result is a glossy, dense, and aromatic coconut mixture with a smooth mouthfeel and a controlled stickiness that allows it to hold together when molded. This freshly prepared filling is discharged from the mixer into temperature-controlled holding hoppers. From there, it is fed through sanitary auger systems into the forming line, where the next phase of production begins, shaping each bar's core. But up next is the forming process, where this cohesive coconut mixture is portioned and molded into the rectangular log shape that defines the inner core of every Almond Joy. This step is handled by a specialized extrusion and forming system. The mixture is continuously extruded through a die system that determines the width and height of the log. These forming dies are custom designed for Almond Joy and produce a consistent cross-section with slightly rounded tops, ensuring a uniform bite and a reliable surface for almond placement. The extrusion head releases a continuous ribbon of coconut mixture onto a moving conveyor belt, and a high-speed rotary guillotine, timed with the conveyor's speed, cuts this ribbon into individual bar-length pieces. The distance between each cut is controlled down to the millimeter, and a sensor-based feedback system ensures that every bar is exactly the same size. After cutting, a short air blast is applied to each log to clear away any stray coconut flakes and ensure clean edges. As the bars are cut, they enter a cooling conveyor that travels through a tunnel kept at approximately 45 degrees Fahrenheit. The cooling process is essential at this point. Not only does it help the bars hold their shape, but it also stabilizes the sugar syrup binder so that the mixture doesn't slump or deform in the next step. A key consideration during this cooling stage is air humidity. If the environment is too dry, the coconut can begin to crust or dry out. Too humid, and condensation may form, which can affect downstream adhesion with the chocolate coating. For this reason, industrial humidity control units maintain relative humidity levels around 45 to 55% inside the cooling tunnel. Once cooled and firmed, the coconut logs are transferred by conveyor to the almond placement system. Each log must receive exactly 2 whole almonds, neither more nor less, positioned evenly across the top surface. The almonds used in this process are themselves the result of a careful preparation sequence. Raw almonds are sourced from large-scale growers, often in California, and are received at the factory in bulk containers. These almonds are sorted, cleaned, and then dry roasted in large convection ovens. Roasting enhances flavor, reduces moisture to less than 5%, and gives the almonds the crunch consumers expect. After roasting, the almonds are cooled and transported to a hopper above the placement system. Here, they are singulated, separated into single file, and guided into individual almond placement arms. These arms are controlled by a vision-guided robotic system that tracks the position of every coconut log in real time. Using photoelectric sensors and high-resolution cameras, the system places each almond with millimeter-level accuracy on top of the log. The almonds are pressed into the surface just enough to adhere without sinking, and an inline inspection system checks that every bar has precisely 2 almonds aligned correctly. Any bar that deviates from this standard is removed from the line for manual inspection or rework. Now it's time to go into the chocolate enrobing stage, which marks the beginning of the transformation from a basic assembly of ingredients into the finished, glossy, consumer-ready candy bar. This process involves fully coating the almond-topped coconut cores with a layer of milk chocolate. But this is no ordinary chocolate. It has been specifically formulated and tempered to provide the right snap, shine, and melt-in-the-mouth texture that defines the Almond Joy eating experience. The chocolate is stored in holding tanks maintained at 110 to 115 degrees Fahrenheit and stirred continuously to ensure it remains fluid and free from separation. Before use, the chocolate is tempered through a process that heats, cools, and reheats it to align the cocoa butter crystals in a stable form. Proper tempering is essential as it prevents fat bloom and gives the coating its glossy finish and clean break. The tempered chocolate is pumped into an enrobing machine, which dispenses it in a continuous curtain across the width of the conveyor belt. As the coconut and almond cores pass underneath, they are fully submerged in the falling sheet of chocolate, while a bottoming unit applies a layer of chocolate to their underside. Immediately afterward, a series of air blowers remove excess chocolate, ensuring a uniform thickness and revealing the shape of the almonds beneath. What emerges is a fully coated bar that looks and feels like the final product, but still needs time to set. That step begins as the bars enter a temperature-controlled cooling tunnel, and that's where the next phase begins. Inside the cooling tunnel, a meticulously engineered, climate-controlled chamber extending over 30 feet in length, the freshly enrobed Almond Joy bars begin their chocolate setting phase. This tunnel is one of the most crucial parts of the process, ensuring that the tempered chocolate coating transitions from a glossy liquid into a solid shell with the perfect texture and finish. The chocolate must cool at a precise rate, not too fast, which could result in cracking or sugar bloom, and not too slowly, which could cause the cocoa butter crystals to misalign, leading to dullness or fat bloom on the surface. The tunnel operates at an ambient temperature between 45 and 55 degrees Fahrenheit, and relative humidity is tightly controlled around 50%. High-efficiency fans circulate cold air evenly across all bars on the conveyor. and temperature sensors track minute variations along the length of the tunnel. The speed of the conveyor is carefully synchronized with the chocolate's crystallization curve so that the bars spend just the right amount of time cooling, usually between 7 and 12 minutes, depending on environmental conditions, line speed, and chocolate thickness. During this stage, the chocolate coating fully hardens around the coconut and almond core, creating a glossy, smooth outer layer that locks in moisture and flavor. The almonds, having been gently pressed into the top of the coconut before enrobing, remain clearly visible through the chocolate shell, creating the bar's iconic bumpy silhouette. As the bars exit the tunnel, they are now fully formed, with all primary ingredients integrated and stabilized. But the next phase, inspection and quality control, ensures that only perfect bars make it into the hands of consumers. The next step is the multi-layered inspection and quality assurance phase, a critical junction in the Almond Joy manufacturing process. Here, each fully cooled, enrobed bar passes under a series of digital scanning systems equipped with high-resolution cameras and sensors that detect inconsistencies in shape, size, and appearance. These systems analyze every bar in real time using image recognition algorithms trained to identify surface defects, incomplete chocolate coverage, missing almonds, or any signs of misalignment. Each camera system captures dozens of images per second, creating a detailed digital fingerprint of each bar. If a defect is detected, such as an air bubble on the surface, a chocolate smear, or a misaligned almond, the bar is automatically rejected using a quick puff of compressed air that directs it off the main conveyor into a designated collection tray. Rejected bars are recorded and analyzed in quality control logs to monitor trends and flag any upstream issues in real time, like syrup inconsistencies or almond placement variances. Following the visual inspection, the bars pass through an inline check weighing station. This precision balance system measures the mass of each individual bar down to the 1/10 of a gram. Bars that are even slightly under or overweight are flagged and rejected from the line. This strict weight control not only ensures product consistency and consumer satisfaction, but also regulatory compliance, as all packaged goods must meet labeled net weight declarations. These check weighers are recalibrated frequently during production to maintain absolute accuracy, and the results are logged digitally to provide traceable batch records. Next, a random sampling process is initiated where trained human inspectors pull sample bars from the line every few minutes. These samples are taken to a nearby quality assurance room for deeper evaluation. Inspectors slice open the bars and examine the cross-section for proper ingredient distribution, moisture retention in the coconut layer, almond placement, and shell integrity. Taste testing is performed by a trained sensory panel in a separate tasting room to ensure the flavor profile remains consistent. Parameters like sweetness, chewiness, and chocolate snap are all evaluated and recorded in a detailed quality report. Once bars have successfully passed through the inspection phase, they are ready for the next stage, packaging. But up next is the flow wrapping process, where each Almond Joy bar is individually wrapped using high-speed machinery designed to maintain hygiene, preserve freshness, and uphold branding consistency. The packaging film, pre-printed with the Almond Joy logo and product information, is loaded in giant rolls at the start of the packaging line. These rolls are threaded through a series of rollers and tensioners that keep the film aligned and taut as it's fed into the wrapping unit. The bars are spaced and synchronized onto a conveyor lane and fed into the flow wrapping machine, which envelopes each one in film and seals it at the sides and ends using heated crimping jaws. These jaws press the film together and apply controlled heat and pressure to create airtight seals that are strong yet easy to open. The sealing temperatures are carefully monitored to avoid overheating the chocolate within, as excess heat could cause the surface to dull or soften. Each wrapped bar is then passed under a thermal inkjet or laser coder, which prints the best before date, batch code, and production time directly onto the wrapper. This traceability information is vital in case of recalls, inventory tracking, or shelf life analysis. Vision sensors verify the presence and clarity of the code, and any missing or illegible codes trigger a rejection mechanism. The speed of this entire process is remarkable. Modern flow wrappers can handle upwards of 500 bars per minute, all synchronized perfectly to match the upstream enrobing output. Once wrapped and coded, the Almond Joy bars are grouped into retail-ready formats. Depending on the destination, this could mean twin packs, king-size versions, or standard singles in cartons. Cartoning machines fold and glue cardboard sleeves or cartons, then insert the correct number of bars automatically. These cartons are scanned for correct orientation, closed, and labeled with shipping and SKU data. A final check weigher ensures that the total weight of each carton falls within specification, and the completed units are then moved down the line to case packing. The case packing phase involves automated robotic arms or pick-and-place systems that lift finished cartons and place them into larger, corrugated shipping cases. The arrangement within each case is optimized for pallet stability and protection during transit. Each case is labeled with product identifiers, batch codes, and destination information, then sealed and conveyed to a palletizing station. Palletizing robots stack the cases onto wooden or plastic pallets in precise configurations to maximize space and maintain structural integrity during transport. Once a full pallet is assembled, it's wrapped in high tensile stretch film using automated rotary arm or turntable wrappers. This wrapping secures the load against shifting during transportation and also provides a barrier against dust and moisture. Each pallet is then tagged with a barcoded shipping label that includes tracking information, weight, and customer-specific handling instructions. The completed pallets are moved to a climate-controlled storage area within the warehouse to await shipment. Now, it's time to go into the logistics and distribution stage, where the focus shifts from production to coordinated movement and inventory management. Almond Joy bars, like all Hershey's products, are managed within an enterprise resource planning system that tracks production batches, inventory turnover, and customer orders in real time. Based on demand forecasts, pallets are selected for outbound shipment, assigned to specific trucks or containers, and scanned out of the warehouse with full digital traceability. Transport is typically handled using refrigerated trucks during warmer months, as the milk chocolate in Almond Joy bars is sensitive to heat. Temperatures are maintained between 55 and 65 degrees Fahrenheit during transit, and GPS-linked thermal loggers monitor each vehicle's internal climate from origin to delivery. If a truck deviates from its safe range, alerts are sent to both logistics managers and warehouse supervisors to prevent spoilage. Once the bars reach regional distribution centers or retail warehouses, the product is scanned into inventory and routed to store shelves. Retail partners rely on synchronized inventory systems that replenish stock as it sells, often based on point-of-sale data. The entire journey, from Coconut Grove to grocery store, can be completed in just a matter of weeks, but every phase must function flawlessly to deliver a bar that meets Hershey's standards for quality, freshness, and consistency. And even once the product hits shelves, the factory's job isn't done. Ongoing consumer feedback, seasonal demand changes, and promotional cycles influence continuous adjustments in batch sizes, production schedules, and packaging variations. Special holiday versions, multi-packs, and limited time offers are all planned months in advance and require tailored processes, new molds, and reprogrammed machinery, an impressive level of flexibility embedded within an otherwise standardized production system. Quality assurance continues to play an active, ongoing role in the manufacturing of Almond Joy, even after the bars have been wrapped, packed, and prepared for distribution. In fact, Behind the scenes of the main production line, a parallel infrastructure operates continuously to monitor, record, and validate every element of the process in real time and long after the initial production phase. This includes not only in-process checks, but detailed post-production sampling and retention, which are central to traceability, regulatory compliance, and product consistency. One critical ongoing practice is the archiving of batch samples. As bars are wrapped and prepared for shipment, dedicated staff routinely pull random samples from each batch, often one every few thousand bars. These samples are sealed, labeled, and logged with all relevant metadata: the exact time of production, line number, raw material codes, chocolate viscosity at time of enrobing, coconut moisture content, and even almond roast profiles. These reference bars are stored in secure, climate-controlled storage units maintained at conditions that mimic ideal shelf environments. The goal is to preserve these products in a stable state for up to 2 years, during which time they may be retrieved for comparison if any quality concerns or deviations arise. In addition to acting as an insurance policy against customer complaints or distributor queries, these archived samples are regularly tested as part of long-term shelf life studies. Trained quality assurance technicians perform controlled aging studies by artificially accelerating the aging process in heated chambers to evaluate how the product will hold up over time. These studies track changes in coconut chewiness, chocolate bloom resistance, almond crunch retention, and overall flavor integrity. Sensory analysis is conducted by expert panels who evaluate sweetness, aroma, textural contrast, and mouthfeel using standardized scoring systems. This data feeds back into ingredient sourcing decisions and packaging refinements, allowing the team to adjust variables well before any potential issues could reach consumers. Now, it's time to go into the digital control systems that operate silently beneath every piece of equipment, coordinating, recording, and adjusting every stage of the Almond Joy production process. At the core of this system is a network of programmable logic controllers, PLCs, which manage the real-time operation of machinery across the factory floor. These industrial computers are programmed to respond to sensor inputs and control outputs with extreme precision, enabling the synchronization of critical events such as syrup dosing, coconut extrusion, chocolate tempering, and wrapper sealing. For example, if the syrup temperature in the blending kettle falls even slightly below the optimal range of 235 to 240 degrees Fahrenheit, the PLC will automatically trigger a compensatory adjustment in steam pressure. Similarly, if a sensor detects that the chocolate curtain in the enrober has begun to thin, indicating an issue with flow rate or chocolate viscosity, the system can alter pump speed, activate an agitator, or send an alert to the line technician. These reactions happen in milliseconds, ensuring seamless operation with minimal human intervention. All this data funnels into a supervisory control and data acquisition system, or SCADA, which acts as the digital nervous system of the plant. SCADA systems provide centralized visualization of every variable in production, from torque readings in the coconut mixes to conveyor belt speeds on the packaging line. Live dashboards display real-time metrics alongside historical trends, and operators can set control limits to trigger alarms, shutoffs, or automatic corrective actions when deviations occur. Data logging is continuous, with every action time-stamped and stored in redundant backups for audit and analytics purposes. But up next is the role of continuous improvement teams and how they use this wealth of production data to fine-tune the manufacturing process. Rather than viewing each shift as a discrete operation, modern Almond Joy factories treat every minute of production as a learning opportunity. Statistical process control specialists and lean manufacturing engineers analyze massive volumes of data to identify small but significant trends. For instance, if there's a subtle uptick in the rate of chocolate flow variation on line 2 during evening shifts, it might suggest thermal drift in the tempering unit or minor calibration errors in the chocolate pump. These insights allow preventive maintenance schedules to be updated, saving time and resources while minimizing the risk of future disruptions. Some adjustments are made on the spot, while others lead to full pilot testing cycles. Pilot lines, scaled-down versions of the full production setup, allow engineers to test adjustments to temperature profiles, mixing durations, or conveyor speeds without interrupting primary operations. For example, if a new batch of coconut arrives with slightly higher fat content than normal, the pilot team may experiment with modified syrup ratios or mixing times to maintain the same moisture binding characteristics. Results are measured using laboratory tools like refractometers, rheometers, and moisture analyzers. And the most successful configuration is then rolled out to full production. The focus on fine-tuning doesn't stop at equipment and ingredients. It also extends to the behavior of the product throughout the supply chain. Some Almond Joy bars are shipped across the country or even internationally, and that means packaging and formulation must perform under a wide range of conditions. Engineers perform transit simulations using vibration tables and thermal chambers to replicate the effects of long-distance trucking or air freight. These simulations allow packaging specialists to evaluate wrapper integrity, seal strength, and chocolate stability under heat and motion stress. In cases where performance can be improved, new materials or layering structures are proposed, often months before the consumer ever sees the final package.